Sorry?
No, just a couple of more minutes and we will start.
Yeah, sure, we can wait. Yeah. It's very amazing how good the connections are these days. I mean, I'm in Normandy, as I said. This is country house of my parents, and it used to be very hard to get a connection. Now I have my computer, my iPhone, and the iPhone communicates directly, and there's no problem.
Wow, very good.
Well, my internet connection is not so good. It goes off.
No?
Yeah, it's not so good.
It's at home.
Yeah, it's at home, yes. In fact, yesterday, during 2 talks, I lost contact and then came back after a couple of minutes.
I couldn't listen to all the talks, but all the talks I listened to, they were perfect. Yeah, there was no problem.
Only in case of one talk that was this interruption. But it happened twice though.
Yeah.
Okay, I think probably we'll start this session. It gives me great pleasure to chair this session on the day of Raghunathan's 80th birthday, that is today. So we will have a felicitation later, but here's wishing him all the best in the years to come. And our first speaker today is Professor Raghunathan from CNRS and Université Paris-Saclay, or say, I suppose that was an old name. Of course, he's also a very good friend of TIFR with plenty of lots of collaborators. And he has visited.
Yeah, also the old name.
Yeah, okay. Visited us an innumerable number of times in the past and graced us with lots of lectures and other colloquium and seminars. So he will speak on local global principle for constant reductive groups over arithmetic curves. So over to you, Raghunathan. Yeah.
All right, thank you, Rajan, and thank you very much for the invitation. I'm happy to be here on this day, specifically this very day where Professor Raghunathan was born. My encounters with, I suppose I met Raghunathan the first time I came to India, which is 1984, but then there was a rather we had let's say a mathematical intersection. Running from, I looked at his papers, probably the first paper which is connected to some things I've been thinking about with 1978, and there was a series of papers on the torsos over the affine line and affine space, which inspired me and my collaborators very much. And let me mention one specific thing, which is the paper with Hungarian, where we worked on the so-called Grothendieck conjecture. Where in fact we started, Younger and I started working on this, and work went quite far. But then at some point, Raghunathan gave us a crucial help for that paper. So okay, that's I want to say. And in fact, what these papers which he wrote, also the paper with Raghunathan, has inspired many people. And let me mention also the work of Philippe Gilles in this direction and others. All right, let me start the talk. So the talk, local global principle for constant reductive groups over arithmetic curves. This is after joint works, 2 papers in particular with David Harbater, Judah Hartman, Danny Krashen, Paramala, and Suresh. So what is a semi-global field? So let me write down a definition. You start with a complete discrete variation ring. The field of fraction is capital K, and kappa is a residue field. The original example of interest is the case of a p-adic field. Okay? And then one considers a smooth projective geometric integral curve over the field K. And the function field of such a curve is called a semi-global field. Okay? It's global in the direction of the curve, it's local in the direction of the field. Such a curve admits a regular projective integral model, and many models. And one calls such a model a normal crossing model if it is, well, a 2-dimensional, regular, projective, flat, x over r, with generic fiber x over k, and one demands that the special fiber, the reduced special fiber, is a union of regular connected curve which intersect transversally. And it's been known for many years that such models exist for a curve over a field like K. Okay, that's the model of a semi-global field. Okay, now if you have a semi-global field, you can look at the various evaluations on that field. So if you have a specific model, you look at the set of codimension points on this two-dimensional scheme, and you have two types of such points: the closed point of the generic fiber, and so the residual field there is a finite extension of the complete field K, and also you have the generic points of the components of the special fiber, and there the residual field looks differently. It's the function field of a curve over the residual field kappa. Okay, to any such point of either sort, you have the local ring, which is of course the DVR, and we denote FV, the completion of F with respect to V. And then when let's omega curly X to be the set of condition points of X, or if you want, or the associated discrete variation rings, or the discrete variations. And then when let's omega F to be the union of all the possible omega curly X for all the normal crossing models of X over R. If you think, basically, you can think of all the possible discrete variation rings on the function field, which occur as a point of coordination 1 on some model. Right, so that's the set of variations we're interested in. And now we look at the reductive group over the field F, over the semi-global field F. And we're interested in what we denote by SHA curly X FG, the set of homogeneous principal homogeneous spaces under G up to isomorphism, which locally at all the completions corresponding to points of connection on X are trivial. And then we have SHA FG, which is the same, except now you look at the homogeneous spaces, principal homogeneous spaces over F under G, which at all the possible discrete variation rings of geometric origin become trivial. Okay, and that kernel, which is just a set, express the possible lack of a local global principle for a principal homogeneous space under G over F. And let me remind you that a principal homogeneous space under a group over F, over any field, in fact, is trivial if and if it has a rational point. Right, so this is SHA, and we're interested in, okay, in this set. Okay, okay, what is the motivation? Motivation is there is some analogy with local global problems over number fields, which you have heard of in Paramala's talk. And also, it's a natural. You might ask, why bother about these semi-global fields? Well, it's an intermediate problem on the way to local global problems for function fields of varieties of number fields. Okay, so to give a concrete example, if you take a function field in one variable over a total imaginary number field, one wonders whether a quadratic form in 9 variables over such a field has a 0. Now, if you replace total imaginary number field by p-adic field, Parma and Suresh proved that any quadratic form in 9 variables over such a field has a 0. So this is an intermediate step. And of course, you try to get afterwards, you would want another local global principle. But that's harder. Okay, so for the time being, we're modest, and we look at this case of semi-global fields. And that case already presents challenges, namely to find classes of groups for which SHA FG is 1, okay, by analogy to what we know about number fields. So for instance, for number fields, we know that if you take a semi-simple group of a number field, SHA need not be trivial, as Paramala reminded you, but SHA is trivial if G is simply connected, SHA is trivial if G is adjoint, SHA is trivial if the function field of G is purely transcendental. Okay, so we're asking in this context whether we have similar results. And if not, we want to produce explicit counterexamples to local global to the local global principle I meant here. Okay, so to remind you, once upon a time, Sarah gave the first counterexamples to the local global principle for semi-simple groups over a number field. Okay, this question whether SHA FG is trivial or what SHA FG looks like has been investigated a lot in the case of a semi-global field where the ground field capital K is a p-adic field. And so Paramala told you many results in that direction in her talk. So now we want to discuss the general case in the present talk. So to discuss the idea of discussing the general case, that is replacing p-adic field by function field, fraction field of a complete DVR with arbitrary field, came up in work of Harbater, Hartmann, and Krashen. This is a method which was started around 2009, and it's called the patching setup. Actually, like anything in mathematics, it's got a longer history. But what Harbater, Hartmann, Krashen did at the time is that they managed to define, to produce a theory which was inspired by earlier things like formal geometry, but which stood by itself. You can learn it within a reasonable amount of time. And so here's what it looks like. You start with a complete DVR. Kappa is the Ryu field. K is the fraction field. T is a uniformizing parameter. We have a regular proper integral curve over R, flat, of course. Yeah. And we have the function field, the special fiber, the reduced special fiber, HY smooth, and we assume normal crossings. And now we choose curly P, a finite set of closed points of the special fiber, and that finite set is supposed to contain all the singular points of Y, which, with the assumptions I made, means in fact all the intersection points of the components, and at least one point of each component Y. Of course, if there are at least two components, this is already ensured, but this is to cover the case where the special fiber would be smooth. Okay, so we have this finite set of closed points. And now you take the special fibers, these points. So think of a bunch of smooth curves intersecting in points. You delete the points. And now U are the components of the complement. So these are smooth curves. And when defines RU, one looks at the functions on the model, on this two-dimensional thing, the rational functions, which are regular on this curve U. No poles there, okay? And then RU is the completion with respect to T, and FU is the field fraction of this completion. And there's a quotient map, because this was functions which are regular on U, so you can induce what these functions on U. So you have this function, this reductive map, this reduction map, RU to kappa of U. Okay. Now, this is for U. Now, if I take a point P, one looks at things which are a bit unusual, namely, one looks at the local ring, the complete local ring at P. So that's a two-dimensional regular local ring. And when you use FP, the quotient of this complete local ring. Okay, this is not the topological field. It's the field of fraction of this complete local ring. And then there's a third character. Each time you take a point P in the closure of U, one considers the local ring. So when one looks at the completion, then one localizes at the point P, one takes the completion, and then one takes the field of fraction of this completion, and that's called FUP. So think of P at the edge at the boundary of U, and then you take the local ring, and then you see the branch U going through that point P. And you take the joint point and you complete and take the field of fraction. Okay, so that's a DVR. This one is a DVR. Okay, and then there are natural inclusions between these fields. FU sitting in FP, FUP, FP sitting in FUP, and of course F sitting in everything. Okay, and the field FUP, in a sense, is built out of the fields FU and FP. And the general idea is that you would like to reconstruct F from this situation, the various FU, the various FP sitting in the FUPs for the various U's and P's. Okay. In fact, the inverse, in a specific sense, the original field is the inverse limit of this entire system. That's the gist of the Harbater-Hartmann-Krashen matching method. Right, so the simplest case is this. You take the curve, you take for your ring R, kappa double bracket T, where kappa is in a field, and you take P1, kappa of T. Now, the field of fraction, F, of course, is formal power series in T, add variable x for parameter on P1. Okay. Now you take U to be the complement. So on the special fiber, you take A1 kappa, which is the complement of the point at infinity. So it's spec of kappa of x minus 1. And P is the point at infinity in a special fiber. That's the simplest case. Okay. And now to give you an idea of what these various fields look like, the FP I mentioned is kappa, is the formal power series in T and X. FU is formal power series in T, the dimension parameter on the vertical fiber, over the field kappa of X. This is, you had this, remember you had this reduction map from RU to kappa bracket X. Okay, FU is this field, and FUP is formal power series in X and then formal power series in T, and then you have these various inclusions. The first time you see this, this is a bit surprising, but well, that's what it is. Okay. All right, now let's go to what the original Harbater-Hartman-Krashen result. In fact, let me think. Okay, so the point is this: you take a linear algebraic group over F, you take X over R, this two-dimensional scheme over this complete DVR R, and P as above of this family of closed points, which correspond to basically singular points on the spatial fiber. Okay? And then you define another type of SHA, not the intuitive SHA which we had with discrete variation rings, but SHA with respect to these various fields which we just saw. So you look at H1FG, and then you go to the product for all the points P, this singular points of the spatial fiber H1FPG, and also you take all the various U, and you take product for U of the H1FUG. And what Harbater-Hartman-Krashen proved in 2015, after the original paper of 2009, to which I will come back, is that this kernel here is in bijection with the double coset, which is the product for all the UP of GFF-UP, and then on the left, the product of GFF-P. So each P, which is at the boundary of a U, you send the FP to the FUP. And each U, which has a P in its boundary, you send FU to FUP, so you have the G of FU going to GFF-UP. And so this double coset interpretation, I think people who are familiar with looking at curves, groups over a curve over the complex field will remember such presentations as the double coset. But in that case, that's what it looks like. And this interpretation, this of this SHA, in fact, comes from a closer analysis by Harbater-Hartman-Krashen of the proof of their basic theorem going back to 2009, which is that if you take an arbitrary semi-global field, if G is a connected electric group and its underlying F variety is F rational, that is the function field spirit transcendental, then this double quotient is reduced to 1 point. So the SHA P in that case is 0. Okay, and that theorem at the time being, when they proved that, it struck us as strange because remember, for number fields, we know that SHA FG, if G is semi-simple, we know that SHA FG is trivial if G is simply connected or adjoint or rational. So what they were proving was that local goal principle in the context where the group G is rational, but not in the case when the group G is semi-simple, simply connected. Okay? And in the case of number fields, this result, the SHA is trivial for G rational, was proved, I think, for the first time by Sansuc, but it's really, it comes out of the basic result, which is the case of semi-simple, simply connected. And then you do a lot of algebra and class physics theory to deduce that result, but the original one was semi-simple, simply connected. Whereas in the Harbater-Hartman-Krashen result, what they have is rational directly, saying nothing about the simply connected case. Okay, so this result was used by Harbater-Hartman-Krashen to reprove and extend the Paramalas-Suresh theorem, which I already mentioned, that quadratic forms in 9 variables of F with kappa finite are isotropic. Okay, now let's come back to the original situation which we had in mind, natural one, which is with respect to discrete variation rings. So for G over F reductive and P in X, this set of singular points of the closed fiber, one proves that there's a connection between these various SHA. So the SHA P, the one considered by Harbater-Hartman-Krashen, is included in the SHA corresponding to one model and the points of connection 1. This is for arbitrary G over F reductive. When G over F is better, that it comes from a reductive group over a given regular model, so G over F has good return over X, then one knows better, namely the unions of these various SHA P is equal to the SHA F. So for instance, if you can prove that the SHA P GF are 0 for the group you're looking at, then you get the div0 SHA also is trivial. Okay. And when G comes from, has even better reduction, namely it comes from a reductive group directly over R. So you pull it back to QIDX and then to F, then in that case, all the various SHA coincide. Okay? So the one is naturally interested in can be computed by means of SHA PF, FG, and therefore can be computed by means of this double coset formula. So as I said, well, now I repeat things which I've already said. In the classical field, the basic theorem is SHA KG for G, a semi-simple simply connected group over K. Okay, and the triviality in the case of GK rational is a consequence of that fact. So the work of Harbater-Hartman-Krashen raises the natural question: suppose we have an arbitrary semi-global field, no restriction with the field, not finite anymore. If G over F is semi-simple, simply connected, is SHA trivial. And for curves over a p-adic field, which was the case which actually Paramahansa Suresh and I thought of at the beginning, in that case, in fact, this SHA equals 1 has been proved in many cases, as Paramahansa has explained in her talk. Okay, and the spectacular last results are the ones which she mentioned, namely the case of AN1 when the degree is not square free, and also AN2 with a mild reduction condition on the prime P, which they obtained using the Harbater-Hartman-Krashen technique. Whereas the previous result had been obtained using Merkouev-Suslin and results of Kato on higher class field theory. Okay, so in the case of tori, so in recent papers with this, so these 6 authors, this was the case of tori, and then the paper which is will be unarchived within a few hours or maybe a few days. We have obtained results on SHA FG for arbitrary semi-global fields F over K. That is now the residual field is arbitrary. When in the specific case when the group G comes from R. That is as good reduction, really, very good reduction. So in that case, we're going to use the double coset formula to get very precise information on SHA, but under the condition that the group G is very nice, namely that it comes from R. Okay. So here's the 2 theorems I'm going to mention, and well, the 3 theorems in fact. So the first theorem is for has nothing to do with simply connected. So take K, a complete discretely valued field, R a string of integers, take a semi-global field that is a function with a curve of K, and X a regular projective normal crossing model of R. We assume that the real field is of characteristic 0 here. This is technical. In fact, we could, well, let me ignore this. This is not crucial. We assume that the closed fiber is reduced. And then we assume that the reduction graph associated to Y is a tree and remains a tree under all finite extension kappa dash over kappa. You know very well that if you have a graph describing how the various take the curves, take a point for each curve, and then link two points if the curve intersect. Okay, and you know very well that the situation tends to be quite different if there's a loop or if there is no loop. So here we assume that the closed fiber has no loop, and that also if you take a finite extension of a ground field, and you take R and then you take a R dash, the relation graph remains a tree. And characteristic 0, this kind of condition is easier to check. In fact, then the statement is that under this tree condition on the graph, SHA FG is always trivial. So we have a local goal principle for any group G of R, provided the group G remains a tree after finite extensions. And the proof is quite elaborate. Now, one thing which is not too elaborate, which we knew 10 years ago, is that if you take a good G of R like this, and you do not make this assumption about the tree, if you take an element in SHA, you can actually, it corresponds to a torsor over F, you can actually show that there exists a torsor over the whole X under G. That is a very nice scheme, smooth, over KDX, which is a principal homogeneous under G, which restricts to the given torsor on the J fiber. But that's all. But we don't know anything about, well, it's a torsor, and so what? So what we show in that paper, in this recent paper, is that under this assumption, okay, characteristic 0, which is technical, but this tree condition, an element in SHA-FG can be represented by a torsor, which, when you restrict it to the reduced closed fiber, the entire reduced closed fiber is trivial. Yeah, that's a quite strong statement. Okay. And then when invokes that, so this is the first part of the proof, which is takes a couple of pages. And then when invokes a recent result of Philippe Gilles, Parimal, and Suresh, to conclude that actually the torsor is trivial over F. And their result says that under suitable conditions, which are fulfilled here, if you have a torsor over curly X under G, if you have two torsor under curly X under G, which on the special fiber are isomorphic, then on the model, they're everywhere locally Zariski isomorphic. And this is really a quite subtle theorem. Okay, so now we have a positive result on this question for SHA. And now I want to discuss the counterexamples. And let me recall the notion of R equivalence. So given a connected algebraic group G over field K, the set of points in G of K, which you can connect to one by, roughly speaking, an A1. So the set of points such that exists an F morphism U goes to G with U open in P1K and both EG and P in the image of a set rational point. These points, which you can link to the origin by just one P1, roughly speaking, they actually build a normal subgroup G of K. This is a lemma of Philippe Gilles, in fact. The quotient by this subgroup is denoted G of K mod R. So what do we know about this notion? If we take a connected rotated group of a G of K and the covariance dimension of K is at most 1, we know that G of K mod R is always trivial. We know that our tori over G of K mod R is not 1. And for G semi-simple simply connected, we know that G of K mod R is 1 if combination is 2 in many cases. In fact, this was reported on in a paper which Philippe Gilles, Parimal, and I wrote on the occasion of Raghunathan's 60th birthday. So there are many cases where you can prove this. The case of covariance dimension 3 is a mystery. And in combination 4 and covariance dimension 4, there exists such semi-simple simply connected group with G of K mod R not 1. I'll say more about this in a minute. Okay, so now theorem B in our recent papers says the following. Take a semi-global field, as usual, with a good model. Take a reductive group over R, and we assume that the closed fiber is reduced and is very special. I mean, it consists of copies of P1 kappa, meeting at kappa points and forming M cycles. So at least M is 1, you would have one loop. And also we assume the characteristic is not one of the bad primes for the group G. Then we can measure exactly SHA-FG. SHA-FG in this case is in bijection with the quotient of G of kappa mod R, kappa is the residual field of R, to the power M, M is the number of cycles, by simultaneous conjugation by G of kappa. So you on both sides. So you take an element G and you conjugate simultaneously G1, Gm. Okay? If G of kappa mod R is commutative, this quotient is nothing but G of kappa, the action is trivial then, and the quotient is G of kappa mod R to the M. And the side remark is that it's an open question whether G of kappa mod R. Okay, using theorem B, one gets a negative answer to the question on semi-simple connected groups over arbitrary semi-global fields. Namely, there exists a field kappa, homological dimension 4, a semi-simple simply connected group G over kappa. And then we look at this group over kappa double bracket T, and a geometrically connected curve over K equals kappa double parenthesis T with function field F, such that SHA-FG is not 1. Okay? And more precisely, here's the field, the residual field we take iterated formal power series 4 times. Okay? R is kappa double bracket T, K is the field of fraction, and then D, for D, we consider a central simple algebra, which is the tensor product of this 4 quaternion algebra, which we have from A, B, C, D, and G is SLD, given by the equation reduced norm is 1. And for X, we take a regular model with special fiber consisting of a triangle of P1 kappa intersect transversally and rational points, the simplest loop you can think of. And to produce the required counterexamples, it remains to recall that there exists G over such a kappa, which have the property that G of kappa mod R is commutative and G of kappa mod R is not one. Okay, and that's a consequence of two things. Result of Platonov back in the beginning of the 70s. If you take iterated formal power series 4 times and you take D equals AB times CD over that field kappa, the quotient of the group of reduced norm 1 element by the commutative subgroup of D star is non-zero. And the other result, which is Voskresensky using the result of Platonov, if D over K is a central simple algebra of field K, and you take G equals SLD, then G of K mod R is just SK1T. Okay, so in that case, we get G of K mod R non-trivial, and we apply that to, this is our field kappa, here you see, kappa double minus T, and X, the curve I mentioned. And I wanted to say a few words about the method of proof, but I think my time is over, so I'll stop here.
Many thanks for your talk, Raghunathan. So are there any questions from the audience?
So, thank you. Can you hear me?
Yeah, we can hear you. Yeah. I just wanted to listen. Okay. Are there any questions from the audience? Okay, if not, we'll thank Professor Raghunathan once again. And if there are any questions, I think people are free to use the chat mailbox and post the questions directly to Raghunathan, or if I say it, I can forward it to him. One of us, any of us. So thank you. We'll meet in 10 minutes time. So
see you then.
Thanks. Thanks. So how is the situation in France?
Well, the last 2 days, I think 2 days ago, they decided we should have a pass. Yeah, you know, a pass that we have the vaccination to enter cafes, cinemas, and also the train. It's quite typical of France. We need the pass to take long distance trains, but not short time trains. I love this.
But you need the pass to enter a
Hello, Jean-Louis. Hello.
Yeah, the pass is either hello, Kosik. The pass is either on the telephone, or you can have it on a piece of paper.
Hello. So since I have not talked, hi. Can we, in speaking to the chairman, can we check whether my sharing screen works, please?
Yeah, you can. Is it Jacob Glass?
Just to check, because in the past,
Yeah, so you have a question. Is there a classification of DVRs for semi-global fields?
So excuse me, can we check whether the system works?
Yeah, you can chat. Of course, you're free. The floor is open to all.
Oh, I am free, but I don't know what happened there.
So,
sorry,
Rajan?
Yeah. There is a question for you.
Yeah.
You saw the question.
No, the answer is this: is that of course, people have been considering whether the various shas, how the various shas behave, because there are also discrete variation rings which do not come from models, for instance. I mean, so there's a paper by 4 or 5 authors. I hope I will not forget one. There's Harbater, Krashen, maybe there's one more. Anyway, some people among there's Harbeiter, Krashen, Hartmann, Florian Popp, and Kermaker. So they have a paper comparing the possible SHAs with respect to all the possible valuations you could think of, even the non-discrete ones, of course, on a semi-global field. So there are many, to answer the question, there are many possible valuations on such fields, and this has been studied by these people. And the paper has been published. I don't know where, but it's been published, yeah.
So do you see my screen? Do you think it works?
No, it doesn't work.
So you see, that's why I wanted to check, because I don't know what to do, because I started the sharing screen, but it seemingly doesn't work.
You can restart and see.
Yeah, you need to go to the app. Yeah.
Yeah, now we can see it better.
Do you see? No.
It's
so
again
what do you suggest to do?
Suri, Soumya,
Yeah, Soumya, can you tell us?
Yeah, it is. I mean, it seems it's getting shared, but then you need to open the app which we will use. Yeah, it's shared. Can you go to the PDF reader or whatever app you will use?
Now you see the thing.
Yeah.
Is this fine?
Yes.
Yeah.
Okay, thank you. That's good. So please give me the start when you wish.
Okay.
Thank you.
Thank you. Yeah. Yeah. So we will meet in. Yeah, in 5 minutes. Is that fine? Yeah.
Yeah. But I do not change anything, so to be on the safe side. Thank you.
Yeah. No, yeah, it's fine. Yeah, it's great. So how are you, Professor Zania? I haven't.
Hello.
It's a long time since maybe the Indo-Italian conference, long back.
Yes, I remember well, of course, yes. And then we were also in email correspondence about the problem of common interest.
Right.
If you visit Europe or Italy, let me know, and maybe we can meet again.
Oh, thank you. Yeah.
In Pisa, if you wish.
Yeah. Okay. Yeah.
Now it is difficult to make any plans, of course. Still difficult.
But is the situation now better, or is it still?
Yeah, I think it is similar to France. What Jean-Louis said a few moments ago.
Yeah.
So we also have a pass. I am optimistic. However, we don't know.
Yeah.
The vaccine seems to be effective because, so I think that if people eventually believe in the vaccine, then we are out of this. I think so.
Yeah.
But many people still are skeptical.
Yeah. But has Italy got what, 40%, 50, 60% vaccinated, or? And
about, yes.
In the eligible age groups. Yeah.
Yes, a big group. But now I think this is a proof that the vaccine works, that if what they say is correct, 9 out of 10 people in hospital did not take the vaccine.
Okay.
So to me, this is proof that it works. If the numbers are correct, of course, this I cannot check. So you please tell me, of course, when I
just a minute.
Start.
Yeah, I think.
Thank you.
Yeah, no, it's just.
Sure.
Okay, so our next speaker is Professor Umberto Zanio from the School of Normal Superior di Pisa. So he will speak on, he will speak on bounded generation in anisotropic linear groups. So Professor Zanio was the host of the Indo-Italian number theory meet long back in 2012. And it was really a pleasure to have met him and to have had this interaction, the Indo-Italian. It's a bit sad that such meetings have not occurred after that, but we hope it will start once the COVID gets lifted. Thanks, Umberto, for a very nice meeting those days, go over to you for the talk.
Thank you very much for reminding this. It is a pleasure for me to remember. And thanks for having been present on that occasion. And of course, I thank all the organizers and persons involved for inviting me in this conference. I am honored to speak in it. So, as the title says, I will speak about bounded generation in anisotropic linear groups. And the first, let me recall, even if it may be known to most or all, what bounded generation means. First, this is a definition which may hold in every abstract group, and I view it as a strong form of finite generation. So the definition is that a group gamma is said to be boundedly generated BG, if there exist finitely many elements of gamma, gamma 1, gamma r, such that each element of gamma is a product of powers of gamma 1, gamma r in this order. So this is important. So whereas, of course, for being the gamma i's to generate, we can do products of them in any order. But now we prescribe to do in this order, and we allow any power. So this is a strong form. Let me give some examples, just to figure out what the notion means. Every virtually abelian, by virtually I mean a group which has virtually with some property, means that there is a subgroup of finite index with that property. So every virtually abelian group, if it is finitely generated, it is also bounded generated. And this is trivial to check. And less trivial, but still true, is that this holds also for a virtually nilpotent group. So these are the first examples of boundedly generated groups. And so nilpotent suffices plus the finite generation. However, for instance, solvable does not suffice together with finite generation. There are examples of solvable groups finitely generated but not boundedly generated. However, this suffices if when we exhibit solvability filtration, if all the pieces are finitely generated and boundedly generated. In fact, an extension of groups with bounded generation has itself bounded generation, which is very easy to check. So this is a second remark. And the third remark, for instance, a result by Malchev, it follows that every solvable subgroup of GLN-Z has bounded generation. So, for instance, for solvability suffices inside such arithmetic group such as GLN-Z. So let me go to our context, which indeed concerns linear groups, gamma, and by which I mean subgroups of some linear algebraic group, points defined over some field K, assumed to be in the whole talk to be of characteristic 0. So let me do some remark on the relevance of the condition of being bounded generated to see that this notion is may appear perhaps artificial, but it seems not to be the case because it has been found to have important consequences towards several questions. And among these, I mentioned work by Lubotsky and independently Platonov and Rapinchuk, 1992. They proved the congruent subgroup property, which of course has been studied by many now classical property. And they proved that this congruent subgroup property for certain arithmetic groups and provided the bounded generation holds. So the bounded generation was a crucial ingredient for their proofs. Another result by Shalom Willis, they used crucially bounded generation for proving the Margulis-Zimmer conjecture, which I do not recall, and actually I'm not even familiar, but it is for experts in the field a very, very important conjecture, a bit technical to state, for certain arithmetic subgroups of Shirley groups. And then another thing that I recall is further implication of the bounded generation appearing work by Avery, Lubotsky, and Meir. Let me give some examples of when bounded generation holds. For instance, landmark result in this topic is Carter-Teller, 1983. They proved bounded generation for SLN over a ring of integers in a number field. And this holds for n at least 3. And actually, they proved bounded generation by elementary matrices, which are matrices with ones in the diagonal and just one other entry being 1. So, in particular, unipotent matrices. For n equal 2, this holds if and only if this ring of infinite unit group, as has been proved by Morgan, Rapinchuk, and Suri in 2018. Somewhat classical examples of bounded generation for somewhat classical arithmetic groups. And let me make a remark that bounded generation allows, in particular, to parameterize polynomially the group SLN of this ring of integers. In the sense, what do I mean by parameterize polynomially? That there is a surjective polynomial map from in several variables that evaluated on the ring of integers produce all elements of the group in question. And we may allow here in the slides, they have only one polynomial map, but we may weaken the condition and allow a finite number of polynomials map. And I mentioned this because this follows trivially from bounded generation by unipotent matrices as for SLN-O. So if we have bounded generation by expanding each power, we get a polynomial, and so we have trivially a polynomial parametrization. On the other hand, polynomial parametrization have been studied separately and independently. There was even an old question of Skolem about parametrizing SL2, and much work has been done. And for instance, even for n equal 2, when we do not have bounded generation, except if the ring has infinitely many units, still there is a polynomial parametrization as shown by Wasserstein over Z, and then Larsen and Nguyen later recently extended to the remaining rings, also for n equal 2. And this in particular shows that the polynomial parametrization does not imply itself the bounded generation. So there are two important properties that are quite related but not equivalent. And the result, last mention on a known result, the result by Carter-Teller was extended by Tavgan 91 to all Chevalier groups of rank greater than 1 and to most quasi-split groups. So we have plenty of arithmetic groups with bounded generation property. And so these and some other results raised many mathematicians working in the field raised the expectation that the bounded generation property could hold in even rather greater generality. Now, going more specifically into the context of the work that I want to describe briefly, work in common, as was in the title, with Pietro Corbaia, Rapinchuk, and Jim Boren. We studied a case, so I have mentioned the generation of SLN was by unipotent matrices, but on the contrary, we study bounded generation with semi-simple matrices. And this would be needed for other potential applications of the bounded generation property. Indeed, there are groups which contain, there are groups of the type of GL and K that contain only semi-simple elements. So this is the motivation for concentrating on bounded generation with semi-simple. And I shall call anisotropic any subgroup of this kind. The usual definition is different, but it may be proved, although non-trivially, that it is for the groups in question equivalent to the one I am giving. So for simplicity, I shall call anisotropic any subgroup of GL and K containing only semi-simple elements. And I shall speak of the bounded generation only for these groups. So let me give some examples. A trivial case is the virtually abelian groups finitely generated by semi-simple matrices. That, of course, is, well, that is an anisotropic group, and if it is finitely generated, it is boundedly generated. Then other less trivial examples, definitely non-trivial, are, for instance, quaternions of norm 1 over certain rings of S integers. Again, here we have only semi-simple elements, and the same holds if we replace quaternions with other division algebras. And then another example, I have in mind is the case of orthogonal groups of quadratic forms not representing zero. That is important. And that gives rise to anisotropic. Mayer's theorem, so we have to restrict to low rank, but we may get many more examples if we work over number fields or over rings like Z of 1 over n. So there is plenty of examples of arithmetic groups which are anisotropic. So I again go back as a remark to the former observation about polynomial parametrization. And in this case, if our group is boundedly generated by semi-simple elements, then the parametrization occurs, but with purely exponential polynomials. So this is a bit different, but there is a dichotomy in the theory also of Diophantine equations and other theories. Somewhat both kinds of objects appear polynomials on the one side and purely or non-purely exponential polynomials, as in the theory of linear recurrences. And let me recall, for instance, Matyasiewicz in the solution of Hilbert problem reduced certain purely exponential Diophantine equation to usual one. And the same dichotomy appears on considering integral points on curves of genus 0, for instance. If the number of points at infinity is 1, then we get integral points with polynomials. And if the number of points at infinity is 2, then we may get integral points by exponential polynomials. And similarly in higher dimensions. So the polynomials are quite different from exponential ones, but there is this link, so to speak. And together with other observations, there was expectation that some non-trivial finitely generated anisotropic groups over rings of S integers would still satisfy bounded generation. So the object of the joint paper with Korvaya and Rapinchuk is to prove few results which instead show that there are strong limitations to the bounded generation in linear finitely generated anisotropic groups. So indeed, the purely exponential polynomials lead us to quite different conclusions. So letters above to explain the results. In precision, letters above K be a field of characteristic 0, and let gamma in GLN K be a linear group. We have a first result, a theorem joined with Korvaya, Rapinchuk, and Ren. If gamma is boundedly generated by semi-simple elements, then it is virtually solvable. So already this draws a quite strong limitation, quite strong conclusion on the group. And even if it is not anisotropic, so as soon as we have bounded generation by semi-simple elements, then we have a very strong conclusion. This conclusion, maybe let me make a few remarks on this result, that we may even allow one non-semi-simple generator. We have proved this bit stronger result with the same conclusion. And of course, due to the results that I have recalled before, like Carter-Keller, we cannot allow too many non-semi-simple generators because otherwise the conclusion becomes false. And now there is an open question, which is the maximum number of such elements, non-semi-simple, that we can allow in a bounded generation to draw the same conclusion. And the examples show that we can't allow more than 4. So we have proved that we can't allow 1, and still we have the same conclusion. We don't know already with 2. So this is an open question if somebody is interested. And let me remark that, so the theorem draws the conclusion that the gamma, if it is boundedly generated by semi-simple, then it is virtually solvable. But there exist virtually solvable, finitely generated linear groups without bounded generation. We have an example that I don't recall for lack of time, but so this shows that a pure converse does not hold. However, if we also assume that gamma is anisotropic, then it may be proved through general theory of algebraic groups that it is automatically virtually abelian. So if it is virtually solvable. So it has bounded generation as soon as it has finite generation. So the following corollary in practice works. If gamma is anisotropic, then it has bounded generation if and only if it has finite generation and it is virtually abelian. Say that this result is a quick consequence of the previous theorem because a finitely generated virtually abelian has bounded generation, and conversely, the theorem implies that gamma is virtually solvable, and we have just remarked that this property, together with anisotropic, implies virtually abelian. Okay, so in the remaining 10 minutes, I resume briefly the steps of our proof. So a first step is to reduce to linear group over number fields. So we let, for later use, also G the Zariski closure of our group gamma. And we shall consider the Q algebra of regular functions on gamma, and we assume by contradiction that gamma is not virtually solvable, but gamma has bounded generation with semi-simple elements by contradiction. Now, to reduce to number fields, we first argue by specialization. So this G, this gamma is a subgroup of a certain linear algebraic group G, so we may view it inside the GLN. And to reduce to the case of number fields, so the elements of gamma may be matrices with transcendental entries, but it is surely finitely generated by our hypothesis. So, the transcendence degree of the elements is finite. So the idea is quite simple and used in several other contexts to specialize through theorems like the Nustellensatz, essentially. So it is very easy to find specialization which maintain the second property, so which keeps semi-simple elements into semi-simple elements. That is very easy. The first one is a bit more delicate because we have to show that the whole group remains not virtually solvable. So there could be a degeneracy on specializing. However, one can argue with the derived series and use uniform boundedness of its length, which may be proved for virtually solvable groups inside GLN. So it suffices to show that the derived series preserves the length. And this is then again not too difficult matter by specialization to show that this degeneration does not occur at each step of the derived series. And then since it has bounded uniform boundedness, there is uniform boundedness, we can conclude. So we can argue from now on with a group with the same properties, not virtually solvable, with bounded generation with semi-simple elements and defined over with points over a number field. So now a crucial step is this step on the existence of multiplicatively independent eigenvalues. So let gamma 1, gamma r be bounded generation for gamma. They are defined in GL and K, where K is a number field. And they are semi-simple. And we are also assuming that gamma is not virtually solvable. So a first step is to take the quotient by the radical of G0, the connected component of 1 in G. We take the quotient and we work in G prime in place of G. So we may further assume that by doing this, that G0 is a non-trivial semi-simple group. Non-trivial because it would be trivial if gamma would be solvable, virtually solvable. So at this point, we use a theory of Prasad and Rapinchuk, or theory of generic elements, and as a corollary of that theory, we deduce the following important step: the existence of an element of gamma such that its eigenvalues are multiplicatively independent from those of all the hypothetical bounded generators. So what we do, we take all the eigenvalues of the bounded generators, and they generate a group, a multiplicative group, a finitely generated multiplicative group. And what we prescribe is that there is, so we prove with this theory of Prasad-Rapinchuk the existence of gamma such that the eigenvalues of gamma are independent of this group. So no power of them lies in this group. No positive power of them lies in the group generated by the eigenvalues of the bounded generations. Let me here make a pause to remark the independence of values of rational functions. This is a part of the Prasad-Rapinchuk theory, and but there is a link, and then I want to remark this, with a completely different object of study, which sometimes is called unlikely intersections. And it concerns, for instance, torsion points on subvarieties of commutative algebraic groups and extended questions of the same shape. And so this multiplicative independence of values is not unrelated to theorems obtained jointly with Bombieri and Masser, and later refined by Guillaume Morin. So maybe that theory also can be applied to obtain conclusions similar to this. It is curious that a completely different theory of Prasad-Rapinchuk leads to somewhat similar conclusions. Of the setting and conclusion of my proof, we have obtained a matrix, gamma having an eigenvalue, not a root of unity, and such that denoting mu1, mu(s), the eigenvalues of the hypothetical generators, we have this intersection is trivial. Some variety of tori. This is a deep theory. A deep theory. To apply this, we assume that each power of gamma is a product of powers of the gamma i's, which is would be ensured by the bounded generation. And now of course, by expanding, diagonalizing the elements, as we can do because they are semi-simple, we have identities like the one which is displayed. So a power of lambda is equal to an exponential polynomial in the eigenvalues of the bounded generators. So we take in a torus, the equation. The subvariety is just y equal to the polynomial evaluated in x1, xt, and we have a point on that variety. And these varieties, these points, and this point is in a finitely generated group, because the exponential equation holds with fixed lambda nu1 nu t. And we have a theorem that inside the subvariety of a torus, the points in a finitely generated group, their Zariski closure is a finite union of translates of algebraic subgroups, so isomorphic to tori. And this result is quite deep. It goes back to, it may be considered a piece of the Mordell-Lang conjecture for display, you see mentioned. And the origin of all of this is Wolfgang Schmidt's subspace theory. Anyway, with this result, it is not difficult to conclude because we apply the theory and would roughly conclude that this subvariety y equal to qx1 xt would contain, the points would be contained in a torus, and this would contradict the multiplicative independence that we have obtained by the Prasad-Rapinchuk. So I skip the last comments that I had, and I stop here. Thank you very much for your attention.
Okay. Thanks a lot, Professor Zania. I think you probably finished it even earlier than, oh no, half an hour. Okay, yeah. Okay, so are there any questions or comments people would like to share?
May I ask?
Yeah, of course. Yeah.
What is missing? What is such a result in characteristic P?
Yes, this is. Thank you for the question. I really don't know. And besides, there are various steps in the proof, but even the last step, the application of this Diophantine stuff would lead to certainly to other cases and difficulties in repeating the arguments. So, so we haven't thought carefully at this situation, but certainly it would present difficulties in various points of the proofs.
Hello, this is Gopal Prasad. I would like to congratulate you for your great result, and I hope to read
Thank you very much.
your paper sometime once I am done with my current book writing, and really
Thank you.
Wonderful achievement.
Thank you very much. I am flattered. Thank you.
Are there any further questions or comments? If not, let's thank the speaker again. Okay, it's all virtual, but yeah.
Thank you very much for the attention. Thank you.
Thank you.
And the questions and the remarks.
Yeah.
Thank you very much.
Thank you, Professor Zania. Yeah, we hope that you would come to India sometime. You have now visited us.
Oh, that would be great.
Yeah.
That would be great. Yes, thank you so much.
Yeah.
Let us stay in touch when this pandemic will be over.
Right. It would be great to have you here. Yeah.
Great of me. Very honored.
Yeah.
Thank you so much.
Thank you. Yeah. Okay, we will meet in 5 minutes, 5:20. It's 5:13. So 7 more minutes and we'll meet for the next talk. But
Hello, Rajan. How are you?
I'm fine. Yeah, very nice meeting you. How are you keeping? How is your health?
Oh, I'm keeping well. I'm fine. I'm in New York now with Anup. So.
Yeah, right.
Yeah.
How is your wife doing? I heard that she had a surgery or something.
Yeah, she's improving every day, and with therapy and exercise and all that, and she's getting very good attention from the grandchildren and children. So she's very happy here.
That's good, very good.
Yeah, in fact, my daughter's family is also here. So, we are 11 here now.
Oh, okay.
Yeah, so it's
so that's going back to your number of brothers and sisters. You are it's a family now. You can play hockey or cricket now.
Yeah, so unfortunately, I have never played any sport. So, hello, Satyadevji, how are you?
Hello, Rajan.
Oh, hello, Rama. Oh, wow. We are just across the city and we have to meet virtually.
I know.
Satyadev, you have to unmute yourself.
Sorry?
Satyadev, you have to unmute yourself. You said something, but it is mute. You are muted. Unmute yourself.
I think maybe I should send it in chat to you.
I think he's trying, but Professor Satyadev,
Yes. Yeah, I can hear now. Yes. Thank you very much. Yes. So, Gopal Prasadji, how are you?
Oh, I'm doing fine. Everything is
I heard when you were replying to Rajan. So, very nice to see you again after such a long time.
Yeah, must be 30 years. So, I'm certainly a very long time. So, your health is good?
Not really good. I'm on dialysis. Perhaps you know this. So,
yeah, I know this. Yes.
Yeah, modulo that I'm okay.
Aha. So you are in Allahabad?
Yes.
Hello, Margulis. How are you?
Hi, how are you?
Hi, Margulis. You didn't appear. You had not switched on your video for a long time, even while you're attending.
Yeah, no, I'm attending. How I? So there's a small picture of mine. I don't know if it's possible to make it larger. No?
Soumya, can you make Professor Margulis's picture, on the screen, full screen?
No, it's the picture is there. We can see the picture.
We can see you actually.
No, see. Yeah.
Okay.
So, Margulis, I hope you are keeping well.
Yeah, it's okay. Yes, it's still at home. Yeah.
At home in New Haven. I mean, near New Haven.
So you were in New York?
Yeah, I am in New York, and after a long time we could come. With COVID, we had not come here for quite some time.
5:20.
We'll meet at 5:30, They change the lecture timing.
5:20 commitment for half an hour. 5:50. Mudiyo.
At Allahabad now, Ganga, Jamuna are in full speed. They have crossed the danger mark.
What is it?
They are flooding, and they have crossed the danger mark.
Oh my
getting
goodness.
ready. Are you getting ready for floods? Maybe Modi will send you a disaster management team.
It's Prayagraj, right? It's not Allahabad.
So where are you? You are in Harishchandra Institute, or you are staying in the city?
Yeah, I think his network is.
Yeah, I think we'll be probably in time for the next talk.
Yeah.
Probably I would request Professor Breuer to load his file, share his screen. Yeah, that's fine. Great. Yeah.
All right. So let me try to share my screen.
Yeah, yeah. Yeah, that's great. I think that's nice. Yeah, so we have great pleasure in having with us Professor Emmanuel Breuer. I hope I got the pronunciation right, who is at Oxford as the Sadlerian professor. Okay, in direct contrast to the Brexit. But so he will speak on approximate lattices and quasi-crystals. So over to you.
All right. Thank you. Thank you very much for the introduction. Let me thank the organizers for this invitation and congratulate Raghunathan for his birthday. As the title suggests, I will speak about approximate lattices and quasi-crystals. So I will discuss work by Simon Machado, Ehud Ruszowski, and Michael Björklund and Tobias Hartnick. So Simon Machado is a student of mine, and we've been discussing these things in the last few years. He hasn't graduated yet. So, all right, so let me maybe first introduce a little bit the subject. So we all know about lattices in Lie groups, and maybe one of the reasons we study lattices in Lie groups is because they are fundamental groups of interesting manifolds, and we'd like to understand the geometry of these manifolds. But maybe another motivation for studying lattices comes from the fact that there are discrete subgroups in ambient Lie groups or locally compact groups. And they also provide, therefore, tilings of these spaces, and they give many nice pictures in particular. So if we go in this direction of tilings, one may be tempted to maybe remove the property, the condition that the discrete group is a group. So I'm going to tell you about the notion of the Delaunay set. So the Delaunay set in a space, let's say X here, XD is a locally compact matrix space, which I assume is a homogeneous space where I have an isometric group acting transitively. So I really think of the classical example of the Euclidean space or the hyperbolic space, or more generally, you can take a locally compact group with a left invariant metric. And so a Delaunay set is basically just a discrete subset in it, which has two conditions. It's relatively dense. So every point in the space is at a bounded distance from a point in the set. And it's uniformly discrete. So this means that there is a fixed radius such that any ball of that radius contains at most one point from the set. So I'm going to define to give four definitions where I will define a class of Delaunay sets, subclasses, so a hierarchy of more and more precise, constrained family of Delaunay sets. So of course, the Delaunay set is, the notion of Delaunay set is very general, and there is no rigidity at all. So you can just basically arrange points in a way so that they satisfy those two conditions in a very easy way. On the other hand, when people study tilings, they usually impose this second condition here, this definition 2, where they say that the Delaunay set has finite local complexity if additionally you assume that what you see around every point at a given distance has only finitely many isometry classes. Okay, so if you fix a ball around a point in the set, then you see finitely many points, and these finitely many points can achieve only finitely many configurations up to isometry. So we call this FLC, for finite local complexity. And it's a remark that essentially the FLC Delaunay sets in the isometry group of my space essentially correspond to tilings of the space with finitely many prototypes that are translated by isometries, and local matching rules that make sure that you can have only finitely many configurations in a fixed ball. So it's also easy to see that a Delaunay set is FLC, essentially if and only if the lambda inverse lambda is closed and discrete. So it's a locally finite set in the group G. That's just a reformulation of the definition. From this, you can see that already there is some interesting rigidity here, in the sense that the group generated by lambda inverse lambda, the subgroup in G, has to be finitely generated. Okay, so that's easy to see because it's going to be generated by the because you have only finitely many configurations, by the differences between two elements in lambda at a finite large enough distance, assuming that you're relatively dense, you can do that. So you have this sort of property. However, here is an example showing you that this FLC property is still not very rigid. So here's an example. So take a uniform lattice, discrete co-compact subgroup in a product G cross H, and consider a Course-Lie Lipschitz maps from G to H. Suppose you have some like this, and for every point in G, you pick a point gamma G in the lattice, which is at bounded distance from this graph, the graph of phi. And then you project that point to the first factor, and what you obtain is a FLC Delaunay set. So you see that since in different situations there can be many such phis, then you can construct this way many FLC Delaunay sets and many tilings. So the third definition, I'm going to again restrict, given a further condition on the Delaunay set, is that of approximate subgroup. So this is a very general definition which occurs in many branches of mathematics, in particular in combinatorics. So if you have a group G, then a subset lambda of the group G is said to be an approximate subgroup if first of all, you assume that one is in the set and the set is symmetric, lambda is lambda inverse. But the defining condition is that the product set, lambda times lambda, can be covered by finitely many translates of lambda. And so this set X here is a finite set of size at most K, and this K sort of quantifies the quality of approximation. So of course, if K is 1, then you have a genuine subgroup. Otherwise, we have what you call an approximate subgroup. So for this reason, you see that lambda times lambda will be, if you start with a Delaunay set, which is also an approximate group, then lambda times lambda will be locally finite, and therefore it will be FLC. Okay, so the Delaunay sets that are also approximate groups are FLC Delaunay sets. And we'll see that the converse actually does not hold. So for the remainder of the talk, I will say that a Delaunay set, which is also an approximate subgroup, I will call it a uniform approximate lattice. Okay, so an approximate lattice is a Delaunay set, which is also an approximate group. And I call it uniform because later I will define the non-uniform versions. So before I go further, I want to motivate a little bit the introduction of approximate subgroups there by this proposition here, this remark, which is that, in fact, if you have a Delaunay set, which is assumed symmetric, such that the triple product, lambda times lambda is discrete and closed, so locally finite in G, then in fact this implies that lambda is an approximate subgroup. Okay, so triple products are needed, while before for FLC we had double product. Okay, so that's a difference. So if you assume that the triple product is discrete, then it's very simple to check that lambda has to be an approximate subgroup, and indeed, because lambda is Delaunay, you can write G as k times lambda for some compact set k, and therefore lambda times lambda is contained in k times lambda, but the element of k that you get here must be in lambda times to the 3, right? Obviously, and this is locally finite, so it has to be a finite set. Okay, so so that's the third property. So here is an example. An example on the real line. So if you take the real line and you take a number field in the real line, and you look at the set of elements of the number field that generate the number field, and are also Piso Vichaya-Raghavan numbers. Okay, so these are the numbers that have that are bigger than 1 and have all their other conjugates in the unit circle. So this is an example of an approximate lattice in R+. So the fourth subfamily of Delaunay sets is the so-called cut and project sets. So these are obtained in the following fashion. You start with your group G, and you pick another locally compact group H, and you pick a co-compact lattice in G cross H. And then you intersect this co-compact lattice with G cross a compact neighborhood of the identity, W naught, all right? So, and then you project this intersection to lambda, to G, okay? So you have a slice in the product, you have a slice, you thicken it a bit, you look at the lattice points there, and you project to G. So if W naught is large enough, then it's easy to see that this is going to be relatively dense and discrete and uniformly discrete. So this is going to be a Delaunay set, and in fact FLC. And in fact, if W naught is symmetric, then it's actually going to be an approximate subgroup. Okay, so it's really a subclass. So what happens if you change W naught into another W naught prime? Then what you get is a commensurable subset in the sense that, so that won't change things very much, in the sense that every, in the sense that the new cut and project set is covered by finitely many translates of the first one. And everything in this talk, I will deal with things up to commensurability. Okay, so to summarize what we discussed so far, we have defined families of Delaunay sets, and the more constrained family is a set of the family of cut and project sets, which implies that they are approximate subgroups, which implies that they are FLC. So the natural question is to ask what to do. Can these implications be reversed? So let me give you some examples. So here, this is a familiar, on the left-hand side, this is called the pinwheel tiling due to Conway. This is substitution tiling. Here's a triangle with 1, 2, and square root of 5, the length of the sides. And you can decompose it into 5 pieces with the same triangle, just smaller. And you keep going this way, and what you get is a tiling, which by subdividing and blowing up, you get a tiling of the plane. And that's it's easy to see that this is FLC, but in fact, it's not an approximate subgroup. The reason being that the angles, so this angle is not a rational multiple of pi, and so you're going to get a dense set of angles of directions in the size of the triangles that show up. On the other hand, on the right-hand side, you have the so-called Penrose tiling, the famous aperiodic tiling of the plane, and this is an approximate group. It comes from a cut and project construction, as was noticed by De Bruyn in the 1980s. So this is 2 examples. So now let me move on to the second part of the talk, where I will discuss a theorem of Yves Meyer from the 1970s, which says something about these implications. So here, let me go back to there. So the pinwheel tiling shows that this implication cannot be reversed, and we'll be interested in the talk about this implication here. So can this implication be reversed? And we're going to show that in many cases it can. So what Meyer did in the 1970s is that he actually showed that this is indeed, this implication can be reversed up to commensurability for Euclidean Delaunay sets. So he showed the following. So if you have a Delaunay set in Rn, the following are equivalent. To say that lambda minus lambda is uniformly discrete, to say that lambda is an approximate subgroup, and to say that lambda is actually contained in a cut and project set and commensurable to cut and project set. So the equivalence between 1 and 2 are easy. In fact, I think Meyer did, he was first looking at a triple sum here, and Lagarius noted that you can assume only that lambda minus lambda is uniformly discrete. So many proofs of this theorem have been have appeared since. There's a nice paper by Moody that discusses this. But the main point of the proof is to show that if you are an approximate subgroup and a Delaunay set in Rn, then you come from a cut and project construction. So Meyer did this in the 70s, and in between the 1970s and the 1990s, physicists identified in nature quasi-crystals, and they were unaware of the work of Meyer, and later in the 90s, the two communities realized that in fact Meyer had proven this theorem, and then Meyer called such sets quasi-crystals or mathematical quasi-crystals. Why? Because quasi-crystals are those Delaunay sets for which the Fourier transform of the counting measure looks like has pure spectrum, so is a linear combination of Dirac masses. And indeed, he showed that these sets have this property. So the proof that of Meyer is not very difficult, but the main point is to realize that if you are an approximate subgroup, then the injection from lambda to the group it generates, which we know is finitely generated, so because it's FLC, is a quasimorphism. Okay, and it's well known that quasimorphisms in abelian groups can be corrected to actual morphisms, to linear maps. And once you know you have corrected the quasimorphism, then you have a splitting of RK, and this gives you the cut and project construction. So I should mention also that Meyer had a fourth equivalence here in terms of what he called harmonious sets in Fourier analysis. So yes, so the question which I want to address in this talk is a question, set of questions posed by Bjorklund and Hartnick. And the question is very natural, is the following. So first of all, can we classify Delaunay approximate subgroups of Lie groups, so approximate lattices? And second, does Meyer's theorem extend to other groups? So in other words, if you have an approximate subgroup which is a Delaunay set in another locally compact group, does it come from a cut and project construction? And so I gave this problem to my student Simon a few years ago in his master thesis, and he solved it for nilpotent Lie groups. And he showed that, in fact, indeed, Mayer's theorem extends to nilpotent Lie groups, exactly as it's stated. So every approximate lattice in a nilpotent Lie group comes from a cut and protect construction. And a corollary of this is that you may wonder, given a nilpotent Lie group, what are the conditions for it to admit some uniform approximate lattice? And it turns out that this is if and only if the Lie group, the Lie algebra of the nilpotent Lie group has algebraic structure constants. So this is a reminiscent, or it's a generalization of Malsev's theorem, which is proven in the second chapter of Raghunathan's book, and which says that for nilpotent Lie groups, admitting a lattice is the same thing as saying that the Lie algebra has rational structure constants. So yes, so this is for nilpotent Lie groups. The proof of Machado, so by now he has several proofs, but the first proof actually mimics Mayer's proof by looking at the Lie algebra and looking at quasimorphisms in the Lie algebra, showing that they preserve the Lie bracket structure and so on. So, but to tackle other groups, one has to first make an observation, which is on this slide here, and has to do with the notion of good model for approximate groups. So this is a notion which was introduced by Hrushevsky in about 10 years ago in his work on pseudo-finite approximate groups, and which was crucial in later work of Green and Tao and myself, where we gave a structure theorem for finite approximate groups. So, of course, finite approximate groups, you might say, you know, by the definition I gave, every finite set of a subgroup is, every symmetric finite set is an approximate group. But what's interesting here is when you fix the parameter k and let the finite subset be very large, and then you can have a structure theorem. This is what we did. But this work only was concerned with a finite approximate subgroup, while now we are only concerned about infinite approximate subgroups. So this notion is the notion of good model. So the way the structure theorem for pseudo-finite approximate groups was proven was, I mean, deep down, the key idea was to try to build a certain topology on the finite or the pseudo-finite approximate group by essentially building a certain fine structure on lambda, by showing that lambda has, so this is what I explained here, and this idea goes back maybe to the work of André Weil in his work on uniform structures. You're interested in finding a sequence of approximate subgroups of your given approximate group, which of smaller and smaller approximate subgroups that are still commensurable to the original one, and also every conjugate is still commensurable. And so if you have such a thing, then you have what's called a good model, and a good model is a homomorphism from the group generated by lambda to some locally compact group H, such that the image of lambda is relatively compact, and lambda contains pre-images of a small neighborhood around the identity. So this gives you the topology on H will pass on to a topology on lambda, and will therefore define this family of neighborhoods of the identity in lambda, so to speak. So it's very easy to see that if you come from a Cartan project set, and you are now a Delaunay set, which is an approximate group, if you come from a Cartan project set, then the second factor, H, provides a good model for you, because this gives you this topology that you're looking for. And conversely, if you have a good model and you are a Delaunay set, an approximate group, then the subgroup generated by the graph of this good model is discrete. And because lambda is Delaunay, it's going to be a uniform lattice in the product equals H. So actually what we are trying to do is to build a good model for Delaunay approximate groups. Okay, so we at the beginning we had no idea how to do this, and let me now move on to now we of course want to tackle this question for semi-simple Lie groups. And so before I go there, let me just say that we can also define, move away from Delaunay sets and consider non-relatively dense discrete subsets and define this notion of non-uniform approximate lattices. So there are two possible definitions. There is a nice paper of Bjorklund and Hartnick where they discuss possible definitions, what this could be. So there is a very natural one due to Hrushevsky, which is which instead of relatively dense, you assume that it's uniformly discrete, and that there is a, so to speak, Borel, so to speak, fundamental domain for lambda. So it is this condition 2 here. While Bjorklund and Hartnick had a different idea, they thought that maybe we should impose as a condition to be an approximate lattice that there exists a G-invariant measure on the invariant hull, which is the G orbit of lambda in the Chaboty space of closed subsets of G. So it's not easy to see what's the relation between these two conditions, but Machado proved that in fact B implies A. So it's a good name. That strong is a good name. That B implies A. So indeed, yeah. So every strong approximate lattice is an approximate lattice. So it turns out in the end that in certain cases, so for example, for semi-simple Lie groups, the two are equivalent. I should mention also that Bjorklund, Hartnick, and Pogozelski prove that cut and project sets coming from lattices are always strong approximate lattices. Okay, so now I come to the statement of one of the main statements, which is generalization of Meyer's theorem to simple Lie groups. So here is Machado's theorem. So the setting is a simple Lie group. So you have a simple Lie group of higher rank, and you start with a strong approximate lattice in there. And the conclusion is that in fact G lambda is contained and commensurable to a cut and project set. So in other words, Meyer's theorem extends to strong approximate lattices in higher rank simple Lie groups. Okay. So some remarks. So actually, his proof and his theorem I stated in a short version, but it actually works in the aesthetic case where G can be replaced by the product of algebraic groups of a local field where the algebraic each factor has higher rank. Okay. All right. So while he was doing this, Hrushevsky came up with a completely different argument of the same theorem, in fact, a stronger theorem, which in particular, he was able to remove the assumption of high rank. So in fact, also in rank 1, or if you have rank 1 factors, the theorem holds. So this was actually, that it holds in rank 1 was quite a surprise to us, because we thought that maybe in groups like SL2R, you could, you may be able to deform approximate lattices. And it turns out that you cannot, unless your approximate lattice is a genuine lattice. So in particular, this theorem holds, and it holds not only for strong approximate lattices, but it holds for all approximate lattices. So the two proofs are very different. Machado's proof uses ergodic theory, and Hrushevsky's proof essentially uses model theory. So let me say a few things about the proof of Machado. So the idea is to mimic Margulis's proof of arithmeticity, because you see, proving this converse of proving this generalization of Meyer's theorem is essentially a Margulis type theorem, an arithmeticity type theorem, because in the end, because the groups are high rank, and also because just the product G cross H is high rank, then every lattice there we know by Margulis is arithmetic. So this means that every approximate lattice actually has an arithmetic origin. So this is why, hence the name arithmeticity. So the proof of arithmeticity goes through a superiority theorem, which is here, which is essentially just the same statement as Margulis' superiority under these assumptions, except that here you start with a representation of the group generated by lambda, and the dichotomy is either the image of lambda is bounded, not the group generated by lambda, but the image of lambda, or T extends to a continuous group homomorphism. So the proof again is based on Margulis' ideas and using this cocycle. You look at the cocycle by choosing a Borel section from the invariant Hull. So the proof uses quite a lot the fact that the invariant Hull has an invariant probability measure. So it's and the rest is just some comments on the proof, which again, in the case, so you use superiority in at least two places to prove arithmeticity. Also, in the case when you're not Delaunay and you're not uniform, you have to prove that you're finitely generated, and this can be done by using some version of property T for approximate lattices. So maybe in the last minute, I would say one thing about Hrushevsky's approach. Hrushevsky's approach is quite different, and instead of applying ergodic theory, he proves a very general, amazing, very general theorem about arbitrary approximate groups, showing that, of course, arbitrary approximate subgroups do not always have a good model, but he shows that they always have a good quasi-model. Namely, that the map we had before, which was homomorphism, is no longer a homomorphism, it's only a quasi-morphism. And the defect of the quasi-morphism lies in a certain abelian group. So with this very strong theorem, he then is able to prove the arithmetic, the converse to Mayer's theorem, that they are contained in cut-off project sets. And then you can apply Margulis' theorem in its original form to deduce arithmeticity. So I should stop there, maybe mention a few further directions and a list of references for those interested in this topic. Thank you very much for your attention.
Thank you, Professor Broyard, for a very nice, interesting talk. Are there any questions or comments? Okay. If not, let's thank the speaker once again.
I think Professor Gopal Prasad wants to ask something.
I'm just saying that, I tried to learn the theory of approximate groups, but didn't succeed. Maybe one has to make another attempt. So it looks difficult, but, your talk was very interesting. And I hope that this will provide impetus for my attempting again to learn the theory.
Thank you, Professor Gopal Prasad. Thank you.
Nice to see you, Emmanuel.
Nice to see you. Yes, nice to see you.
I have some question. You introduced this Piso-Vijayaraghavan numbers as an example. So, is there some application to such kinds of arithmetic things? There are this conjectures about the smallest Piso-Vijayaraghavan should be bounded away from 1 and such things.
Yes, I don't think there are applications, but maybe it goes the other way. But I think you mentioned talking about maybe the Lamer conjecture. Or
right.
Like that.
Right. Salem number problem. Right.
Right. No, I'm not aware of applications, but certainly I find it fascinating that these PV or PVS numbers show up in this area. Yeah.
Okay.
So yeah, so you can show actually that these approximate lattices always commensurable to, for example, if you're in SL and R, then they would be commensurable to the set of points in SL and R, which whose matrix entries are all Piso Vijay-Raghavan numbers.
Oh, okay.
Yeah.
I also had some other in the, but probably you did mention something about I don't know whether the question is well posed, but is there some harmonic analysis way of looking at this approximate lattices? You did mention something in the.
Yes. So yes. So this is the notion of harmonious sets. Which measures to what extent an abstract character, so group homomorphism, from the group generated by lambda to the circle group can be approximated by continuous homomorphisms. So if this can be done, then this is called a harmonious set, and Meyer showed that the two are equivalent. So being harmonious and being coming from Kata project construction,
Okay.
And being a quasi, what he calls a quasi-crystal.
Okay. Thank you. Yeah. Are there
so there are lots of other interesting questions, such as trying to understand the the Fourier transform or the non-abelian Fourier transform in SL2R. So there's some nice work by Bjorklund, Hartwig, Pogorzelski, a series of papers where they study harmonic from the harmonic analysis point of view, the Fourier non-abelian Fourier transforms of the counting measure on such Delaunay sets.
Okay. Are there any further questions or comments? So let's thank the speaker, and I think there are breakout rooms available. So maybe we are meeting at 6:30, right? Probably I will hand it over to the organizers. That ends the first session, and probably the organizers can take over. You can one can go to the breakouts. So. Yeah, okay. I stop and probably I hand it over to them.
Thank you. Very good.
Okay, the next session will start at 7:10. Maybe we should recall.
Sir, you want me to create breakout rooms for discussion, or is
Rajan, he is asking you. I don't think people are using breakout rooms now, right now.
Yeah, I know. I thought I would leave it to the organizers. I think Suri, you and Dani and Jugal and others probably. If
we can discuss here itself. Again. Breakout rooms may not be.
Yeah, recordings. I mean, recording is stopped now.
Okay.
Paused. Yeah. Probably we can stop. No, it's not possible to stop the live stream. Yeah. Otherwise.
So the next session started 7:10, is it?
Okay. Yeah, maybe I think since it's more than an hour, maybe we can probably take a break. Yeah. Hi, Suri. So how are you?
Fine as can be. Except some teeth are missing now. I think I have to have some dentist appointment.
Oh, how come? What happened? You fell down or something? Or?
Not really a long story, but.
Okay, just the teeth are falling down on the road.
So at the same time, I had to have 8 teeth attended to single sitting.
Hey, where's your son? What is he doing?
Sorry, my son. Yeah. So he's got admission to UC Riverside, mathematics PhD.
Okay.
But last year has been online, so he will probably leave in September. Join there. Vidur.
Oh yeah, Vidur. Yeah, right.
But yesterday he had gone to Chennai for visa. That's why he was not at home. He got back now. Okay, see you at 7:10.
See you then. I will also probably leave now. Yeah. Thanks, Suri. Bye. Yeah.
Take care.
Take care. Yeah. So I will leave now. Yeah. I hope it doesn't close all the things.
No, it's okay.
Hi, Nimish.
Oh, hello, Anish.
How are you doing?
Well, good, good. Good to see you.
Yes, I can't see you yet.
Let's see. I hope there is no problem. Yeah, I did try to keep the video on, but I can't.
I could see you on the first day, you know.
Yeah, yeah.
Hi, Alex. I've not greeted you so far. Let me say hi now.
Oh, hello. Yeah, we talked yesterday a little bit. Let me just log out and get back.
Okay, okay.
Yeah, I don't know why this happened, but.
Raghunathan, you are. It's rather dark over at where you are.
Oh, sorry, I put on the wrong light. One moment.
It's a bit dark.
Yeah.
Hello, Alex.
Is it okay now?
Hi.
Yeah.
Done.
Yeah, good.
Hi. Oh, we are supposed to close the.
Shahar is there. Anish, I am seeing you for the first time. Huh?
Hello, hi.
Maybe you didn't turn on your video.
Yes, I was. I didn't turn my video on. That's right.
Yeah.
I turned it on for the group photo and then turned it on.
Okay.
How are you doing?
Okay.
Come over sometime. We haven't seen you here for a long time.
Still under house arrest. Maybe another 2 weeks. Maybe September 1st is when I will start out. So far.
Okay, all right.
The only place I visited is my son's house. That's all.
Right,
And that to happen 3 times in the whole year. So
my goodness.
From March till now, that's the only outing I've done practically. Because I do go for walks in the morning, but even that I've discontinued because of the rains for some time.
Right, of course, yeah.
They are random walks now.
Hi, Margulis.
Hi.
Hi.
So, there's a small picture of me. So,
sorry?
No, there's a small picture.
Small picture of?
I don't know. Is it possible to make?
We can see you full screen.
Yeah, we can.
We can see you full screen.
You can see full screen.
Yes.
You will see full screen. Okay, I will see myself in small. Okay. Okay, so when I need it, okay, now probably I'll take video off and. Okay. So.
Nimish is back.
Yeah, but I don't know. Let me just share my screen and see if it works at least. It shouldn't be that way. Yeah, which device are you using, Professor Shah? I'm using my computer and it was working. I think yesterday once it caused a problem, but after that, and this is the first time it happened with it.
Your camera is on, but somehow it's not.
Yeah. What
You can try sharing. You can try sharing and see if this file shows or not.
Yes. Yeah, my file shows.
Yes.
Yeah.
But I don't know what's wrong with my video. Video settings.
Soumya, can you help?
Is there a way to change your camera? Maybe it has two webcams or something. One of them.
I'm only logged from one place and not elsewhere. Yeah, only logged from one place, and it happened once yesterday. I don't know why.
Yeah, we saw you for a short while. Yes.
Yeah.
Okay, maybe we can start, and hopefully during the talk it resolves itself.
Yeah.
Okay, so welcome back everyone to this final series of talks in this fantastic conference honoring Professor Raghunathan. So it's a great pleasure to welcome Professor Nimish Shah from the Ohio State University, who is going to tell us about sharp conditions for equidistribution of translates of a subspace of a horosphere by a diagonal flow in the space of unimodular lattices. Nimish, please go ahead.
First, I'm very much honored that the committee chose me to speak here, and it's such a great pleasure to be able to speak on the 80th birthday of Professor Raghunathan. I'm extremely happy about it, and very happy birthday, Professor Raghunathan.
Thank you.
Today, what I'm going to speak was a question that was motivated by a work of Kleinbach and Margulis. So they resolved a Sprint-Zook conjecture on Diophantine approximation using a homogeneous dynamics method. And let me just first say a very special case of what they have proved, and that will motivate what I want to do next. So we start with a group SLNR and lattice SLNZ, and we take a finite, finite interval J, and consider a function which is analytic from J to Rn-1. So this is SLNR, and this goes into Rn-1. What is the use of this function? I'll explain now. You look at a diagonal flow, t to the power n-1, t inverse. This is n-1 times. So that's an element of SLNR. And given any unipotent element, given any element of Rn-1, I will arrange in this manner that I'll put 1 on the diagonal, and here is this n-1 coordinates. And then when I say U of Vs, I mean a curve inside a unipotent group, and the curve is like it's all 1 on the diagonal, but in the upper line there is phi1s to phi n-1s. So this is a curve in this unipotent group, and the unipotent group of this kind, all possible x1 to xn-1, that is expanding horosphere of AT. So when AT conjugates elements of SLNR, these are precisely the elements which get fully expanded by AT when t goes to plus infinity. So what they proved is the following, that given any point in this quotient space SLNR mod SLNZ, there exists a compact set depending on some epsilon. So you start with an let epsilon be positive, and you get a compact set k epsilon in G mod gamma, so that if you look at this trajectory from X, you look at the trajectory of this unipotent group. So this is U of Vs. So it's some kind of curve in Rn-1 here. And you apply that to X and then translate by AT. This curve is parameterized by S. So you look at all those S in this interval J, for which this translate goes inside the compact set K epsilon. So K epsilon is some compact set depending on epsilon. And then the relative measure of so those S which fall into this compact set is bigger than or equal to 1 minus epsilon. That means most of the time, this curve will lie inside this compact set K epsilon. So the G mod gamma is a non-compact space, and K epsilon is some large compact set depending on epsilon, and most of the percentage of your trajectory after translation by AT will fall inside K epsilon. That's their theorem. And there is a lot of history behind this kind of work. That's a work of Margulis and DAE in non-divergence properties, and it was very beautifully used by Kleinberg and Margulis to generalize and prove this kind of theorem. And if you look at it, this curve is exactly equal to, because AT normalize this U of Phi, you take it on the other side, then it will expand this Phi by e to the power nt. That's the these are the eigenvalues you will get here. And so it's a very blown up curve in Rn minus 1, and it becomes very, very long. So as you make your T larger, this base point keeps moving, and this is a very long curve. So in some sense, you may think, will this curve will become dense in this space as T goes to infinity? Or more specifically, if I put a probability measure on this based on this parameter S, just make it a normalized probability measure, and for every T you choose this measure, so you will have a probability measure mu T on this homogeneous space G mod gamma, and this probability measure, what the theorem of Kleinberg and Margulis says, is that this probability measure will converge. So the Kleinberg and Margulis theorem says that there is no escape of mass. Okay, so you look at this mu T, then there is no escape of mass as T goes to infinity. In other words, you give any sequence Ti going to infinity, then after passing to a subsequence, you can show that this mu sub Ti will converge to a probability measure on G mod gamma and in the weak star topology. So the question that I wanted to ask is that, will this measure become a G invariant probability measure on G mod gamma? So answer of this question is yes. In 2009, I proved a theorem that if you take any, so just the meaning of what is weak star convergence is that given any f in compactly supported continuous function on G mod gamma, you take any x in G mod gamma, and you apply this curve phi of s, where s runs over J, and you translate it by AT, and you integrate your function f on this curve from s in J and divide by the length of J. And as T goes to infinity, you show that the integral of your function, so you have this function f on this, and the integral of the function along this curve actually is very close to the integration of the function on the whole space as T goes to infinity. And that's what you want to say. That's called equidistribution of the translates of curves. So what is the most important property of the curve I used here is that this curve phi is an analytic curve, but the condition is that its affine span is Rn minus 1. So this is the condition you needed for this theorem of Kleinberg and Margulis. And this is the most important condition, is that the affine span of the image of phi is Rn minus 1. So it doesn't live in a proper affine hyperplane. So this theorem has interesting number theoretic consequence related to Dirichlet's approximation. So we see that a point X in RK is Dirichlet improvable if for some number alpha less than 1, and for all large T, there exists, so given any large T, you want some integer vector in Zk, so that if you look at its inner product with X, you get some real number, and that real number is very, very close to an integer, meaning when I write this symbol to simplify my notation, when I write the symbol with this kind of bracket, I mean the distance of this object from the nearest integral point. So if it's in a vector space, then it's the nearest integral vector. So here is just a real number, so it's a nearest integer. So distance from the nearest integer is less than alpha times t to the negative k, where the vector q in zk has sup norm less than capital T. This is just the coordinate-wise maximum. So if you bound the coordinate of this integer by t, then you can get approximation is alpha times t to the negative k, where for some alpha less than 1, you fix that and you want it for all large t to this to happen. It's important that you want it for all large t, not some. Dirichlet's theorem actually says, this is the pigeonhole principle he introduced in proving this theorem, is that if alpha is 1, if I put this number equal to 1, then in fact, for every real vector, you will have solution to this inequality. But making alpha less than 1 makes it special. And it turns out that Davenport and Schmidt in 1969 proved that almost every x in RK is not Dirichlet improvable. So in the sense of Lebesgue measure, almost all points you cannot improve this condition for any alpha less than 1. And it turns out that DAE introduced the notion of how to connect Diophantine properties of this kind with orbits of diagonal groups and so on. That introduced a concept, and it's called now DAE's correspondence, and this was very well developed by Kleinbach and Weiss in one of his 2008 paper. And the above, so using DAE's correspondence, one can show that the above distribution theorem says that almost any point on this curve is not Dirichlet improvable. So we know that almost all points are not Dirichlet improvable, but there may be a set of measure 0 points which are Dirichlet improvable. And given a curve in Rn minus 1, the curve itself has measure 0. So you cannot know whether all of those points are actually improvable or not. But you actually prove here that if your curve has the affine span which is equal to Rn, then it is indeed almost all points on the curve are also not Dirichlet improvable. So our more interesting part is the proving the equidistribution theorem, as I mentioned above. But now what is left out is that what if affine span of my curve is a hyperplane, and say it's just an affine line. Suppose my curve is really just a piece of an affine line, which is given by phi s is equal to s comma a1s plus b1 dot 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 an minus 1 s plus bn minus 1. So I'm using the first coordinate of my affine line as just a free variable, and then other variables can be written in this term. So it involves two vectors, a1 to an minus 2 and b1 to bn minus 2, that will determine my line. So one would like to say somehow that if this affine line is like irrational, or maybe it satisfies some kind of Diophantine condition, then you would like a similar kind of equidistribution theorem. And indeed, Anish Ghosh in his thesis in 2006, he extended this work of Langdon Margulis in this direction. He actually obtained certain Diophantine conditions on this coordinate a1 to an minus 1 and b1 to bn minus 2. because phi n is element of Rn minus 1 and first one is S, so there are n minus 2 coordinates here. He made some, very precise results and extended the work of Kleinberg and Margulis on Swain-Zug conjecture, not only for curves spanning whose span is Rn minus 1, but also for affine lines like this, and also for affine hyperplanes like this. So my question now is, what happens if we want to prove equidistribution theorem? I tried this for many years and really couldn't make any progress in this. In different direction, my early result was only for SLNR mod some lattice gamma, or my curves were inside SLNR. But Pengyu Yang in 2019 in his thesis generalized this equidistribution theorem for translates of curve on arbitrary G mod gamma for any semi-simple group G and any lattice gamma. So that was a very beautiful work, and he just did it in complete generality. He described what kind of curves are allowed to get equidistribution, and he described that in terms of certain Schubert varieties associated to AT in the general diagonalizable flow. So the main interesting thing he brought into his this game is Kemp's invariant theory, and that really helped a lot. But before I go to that, let me just recall the general strategy of the proof. So the general strategy of the proof is as follows: that my curve is of course like a curve inside Rn minus 1, and you multiply it by AT, it gets expanded, and it becomes a very blown up curve. Locally, it is very straight, and locally it approximates a unipotent subgroup for a long length. And you can do, there is some very simple twisting argument using which you can almost essentially show that your measure, you can treat a slightly different situation and say that the measure is invariant under a unipotent one parameter subgroup. And once you know a measure on G mod gamma invariant under unipotent one parameter subgroup, you can apply Ratner's theorem. So classification of ergodic invariant measures under unipotent groups. This was actually conjectured by DAE based on Raghunathan's conjecture for orbit closures. And finally, it was actually proved by Marina Ratner in 2000, in around 1990. And she classified ergodic invariant measures for unipotent flows. So you use that classification that tells you how the limit measures can look like. And then you use a technology that was developed in the work of DAE and Margulis in proving non-divergence. And to conclude that if you consider our limit measure, if it does not converge to the Haar measure, but some measure which is invariant under unipotent one parameter subgroup, then you get some kind of boundedness of bounded linear dynamical condition. So you get some kind of representation theoretic condition, which will tell that if you don't equidistribute as you expect, then some linear dynamical condition will occur. What it means is that there is a finite dimensional representation of G over Q and a rational vector P such that, and you get a sequence gamma I in gamma and some number C positive, such that if you take this rational vector, apply gamma I to this, because gamma i's belong to integral lattice, this is a discrete set of points. You apply that to this G where your original point X is G gamma, then you just apply this G here. Because these are up to gamma, it's okay, just choose one choice of G. And then you apply this curve U of S, and then you translate it by A sub Ti. You see, and then you look at sup over S. So the entire curve, if it pushes into some bounded set, then that's the only way you don't get equidistribution with mu sub g. Okay, so this is a linear dynamical condition that causes problem. It's possible that basically you want to say that if you want equidistribution, the p should be fixed by g itself. Then there is nothing happening. Okay, so you want to say this, if this happens, then something very special must be happening about this curve phi and etc. So for example, in my earlier result, we showed that if phi is the affine span of phi is Rn minus 1, then this condition will actually imply that p is fixed by the entire group G. So there is nothing really happening in this condition. And that gave the result. But in general, if this is just a curve, a fine line, then what happens? So in using this kind of Kamp's theory, very recently with Dima Kleinbach, Nicolas Dissexe, Pengyu Yang, and myself, we proved that this theorem for SL3R, and it says that you do have the same equidistribution result provided you have some kind of condition on A and B. So if this equidistribution fails, then you will have a condition of this kind. And if the condition of this kind happens, then you can show that in fact this A and B should satisfy the following Diophantine approximation condition, which says that there exists some constant C positive and there exists infinitely many integers Q in Z, so that if I multiply Q with A and you look at its distance from the nearest integer, then that is less than or equal to C times Q to the negative 2. And the same Q will work for B, and also simultaneously we give the same, same estimate. So this kind of pairs A and B are very few. In fact, the work of Dodson shows that the Hausdorff dimension of such pairs in R2 is just 1. So there is very small number of pairs for which this will fail, and the rest of them, this is true. So you can ask what happens if you work with SLN. So if you, I guess that I didn't check the condition of Anish Ghosh. I think his condition would only require not going to infinity, in which case you can have a stronger, you can have a weaker or stronger Diophantine requirement for it to fail to have non-divergence. You probably would put some epsilon like this and so on. But let's, in our case, it's exactly this one. Now, about SLN, what can you do? So in SLN, many more possibilities than this kind of thing arise. It's a lot more complicated to analyze that bounded Diophantine condition that I mentioned before. And in a almost completed work with Pengyu Yang and myself, we proved the following. To simplify our situation, suppose my curve phi s is just a curve like this in this coordinate. It's just actually an affine line. And then I want a condition on this vector a1 to an minus 2 so that I get equidistribution. So you see, you get equidistribution if and only if this vector A and vector B satisfy one of the following Diophantine or number theoretic conditions. The first condition is very much similar and almost same as this condition. Just that you have A and B are just single elements in SL3, and here now you have vectors. So it's you have inner product instead of multiplication. You have a C positive, so that Q times A in the inner product is less than these numbers. And these powers you get is coming from AT, this power. And that's it. So you have this kind of Diophantine approximation that will be forced on you if you fail to equidistribute. Oh, maybe this is wrong, unless it's wrong. Unless it satisfies any of the following conditions. Okay, so if it satisfies this kind of strong Diophantine condition, then you will not have equidistribution. If it does not satisfy any of the three conditions, then you will have equidistribution. So first condition is the same as before, but a new condition occurs in this higher dimensional case. And the new condition is as follows, that my curve may lie inside a hyperplane defined over a number field K, and this number field K would be such that its index, so it's a real number field, and its index actually should divide n. So if my n is prime, for example, n is 3, then there is no such number 2 case does not occur. And in that case, my line is just contained in a proper affine subspace of Rn minus 1, which is defined over K. So proper affine subspace can be given in terms of matrices, because one matrix will define where the direction, and the other matrix will be translation. So together, all of the coordinates you can choose inside this number field K. So this second obstruction comes from this very specific number field situation, but then there is this number theoretic fact that this field extension, the degree, should divide n. Otherwise, it will occur. And the last condition is can occur if n is even degree, and in that case there will be some a complicated condition involving exterior 2. And if you simplify it, the condition looks as follows. I don't think it's a good idea to go into details, but there are this antisymmetric integral matrix of this kind, and if you multiply A with this antisymmetric integral matrix, and you get a vector, 2D vector, 2D minus d-dimensional vector, and you look at closest integer distance from closest integral point, then that is less than or equal to this number. That happens simultaneously for A, B, and certain determinants involving A and B. So it's a little bit complicated condition, but that can happen only if n is even. And the point is that any one of these condition occurs, then you can definitely not get equidistribution. So it is really if and only if and sharp condition. There is a geometric meaning to all of this. And the corollary is that if my phi s does not satisfy any of the three conditions, then almost all points on my curve are not Dirichlet improvable. Now, Dirichlet improvable is not equivalent to equidistribution. So for example, in the SL3R case, you can actually prove that almost all lines on a non-rational line are not Dirichlet improvable. So all you need for Dirichlet improvability is just to say that there exists a sequence Ti going to infinity for which it converges to R measure, not necessarily for every sequence, but there exists a sequence Ti going to infinity. That makes a much weaker kind of condition. And for that, Diophantine conditions would be different. We have not worked it out in the general case, but SL3R case, you just realize that you really don't have any condition except that your curve is not a rational line. That's it. And what involves in this is the Kemp's invariant numerical criterion to simplify the boundedness condition on the representations, because you see this, I have this boundedness condition for the representation, and this Kemp's criterion allows you to say that if this point, the G orbit of this point is not Zariski closed, then you can reduce it to this V to a fundamental representation and P to be some even exterior E2, exterior EK, that kind of vector. And secondly, from that, using certain ideas of David Simmons and Bruglia, which were communicated to us by Kleinberg and Discrete respectively, both separately and independently, that you can further reduce it to a standard representation. So the game is to reduce your problem from complicated representation to simpler representations, and that gives you the simpler, writable conditions of this kind or checkable conditions of this kind. And so that is one part. And if G orbit is very close and still that kind of things happen, then you involve some theory of minuscule representation and involve some classification theory. And then at some stage you need to use Galois cohomology to get to rationality. And then that takes care of the three possible cases. In particular, for example, if n is prime, then you don't need condition 2 and 3, which are complicated. And secondly, this I only talked about a line, but you can also say that you take a curve whose affine span is hyperplane. And for that hyperplane, you more or less have the same kind of conditions on the defining matrices of the hyperplane, very similar to this. And again, your hyperplane should be contained in a proper affine subspace defined over K, and then this index should divide N and so on. That's a hyperplane case. And third case does not occur if hyperplane is, if it is not a itself a line. If there is no line, if it's a curve, but maybe sitting on some hyperplane, the number 3 case does not even occur. So, and if it's prime, then nothing divides N, so you have no condition. If it's prime, then it's only first condition is needed. And you can say that it's not divisionally improvable, and also you have equidistribution theorem. But here with this, I finish my talk. Thank you.
All right, so that was an excellent talk. Let's thank Professor Nimish Shah for that great talk. Are there any questions or comments?
Bruya wanted me to zoom into slide, but I missed the opportunity to do that.
Emmanuel, do you have a question?
Yeah, can I ask a question?
Yes, of course. Please go ahead.
Yeah, Nimish, I'm Sengupta.
Yes, I know that. Yes.
Yeah, hi. Yeah, so I wanted to know, so in your this thing, you're looking at only one-dimensional unipotent and the one-dimensional subgroups of the split Cartan, right?
No, one-dimensional subgroup of the split Cartan and full horosphere of the split Cartan, this kind of Cartan.
No, but your U of Phi was just
it's just one-dimensional. No, U is U of Phi. U is a unipotent group, whole horosphere, yeah. And I'm taking a curve inside that horosphere.
Yeah,
curve
so
or a line.
Curve, okay, it's a curve in U. But
yes, it's a curve in U or a line in U. Curve was done
earlier.
Curve was done earlier.
Suppose you keep the curve, but you make a group A larger. Will it have any consequence like a simultaneous approximation from the number theoretic side?
Yes. So for a curve and looking at A, but the only kind of A I worked with is the first coordinate is positive and the rest of them are contracting. So the same horospherical, but the diagonal A can vary, and you can have this Minkowski kind of result.
I see.
Non-improvability. Yeah, you do have such a result for curves. We still don't clearly have a result, probably partially have it, but not clearly in the affine case yet, because it's part of the work, good piece of the work. Main ideas are done, but then for this kind of variations, it's not completed. There is a lot of things that can be done. Yeah, so at the moment, that's what.
Thank you. It was a very good talk.
I wish I could switch on my video, but I'm not able to do that.
Are there any other questions or comments? So Nimish, do you have a general conjecture about what should be the right conditions?
No. In fact, we didn't even expect that's these simple conditions. We thought that it will involve all kinds of number fields and all kinds of subgroups containing something here and there, and I thought it would be impossible. Really say we could probably have said some very general kind of things that it avoids closed orbits of groups and stuff like that, but it turns out using some ideas that came with a minuscule representation, there is a nice finite classification of possibilities of stabilizers that we get, and then based on that, we don't have choices left. So it was a very interesting kind of thing. So not that many conditions are needed.
Right.
Yeah, that was a surprise. And these conditions were written only after the work was done. We just couldn't guess before that.
It's really a great result. Thank you so much. So if there are no further questions, let's thank Professor Nimish once more. All right, so the next talk starts in 5 minutes. So see you soon.
Good to see you, Alon.
Hi.
Whose talk is next?
The next talk is by Amir Mohammadi. Amir, are you around?
Okay.
Yeah, I'll stop.
Yes, I am.
How do I start?
Hi, Nimish. Hi, everyone.
Oh,
hi,
Amir.
Anish, hi. So I'm actually gonna join maybe using my iPad too. So let's see if this will work.
Yeah, we can see your screen.
That's good. Now you can see the slides too.
Yes, excellent.
Okay, very good. Well, it's 5 more minutes, right? So,
yeah, maybe more like 3. So.
Okay.
Tough chairperson. Well, 10 minutes, 5 minutes, 5 minutes, 3 or 4 minutes start.
Just அவளை வந்து ஒரு நிமிஷம் மீட் பண்ணி தேங்க் பண்ணிட்டேன். என்னது இது? வாலெட் எந்த கார்டு ஒரு நிமிஷம் வந்து தேங்க்
கொஞ்சம் ஆழம் பேசுறது.
இல்லை எங்க அப்புறமா அதுக்கப்புறம் திருப்பிட்டேன். ஃபெலிசிட்டேஷன் ஒரு நாள் ஆயிடுமே. I told her that if you are on the very much of 2 minutes ask one name on
All right, shall we start?
You're the boss.
All right, okay. All right, so welcome to the final talk of this conference. It's a great pleasure to introduce Professor Amir Mohammadi from the University of California, San Diego, who will tell us about finitary analysis in homogeneous dynamics. All yours, Amir.
Thank you. Thank you very much for the introduction. It's a great honor to be here and give this talk. This being the last talk, I think we should all thank the organizers and the support team for this great conference. So with that, maybe I'll get to the talk. This is a half-hour talk, so I'll try to be brief, maybe even finish before half hour so we can be ready for festivities. Like Anish said, I want to talk about quantitative aspects of flows on homogeneous spaces. This has already appeared at least in two of the talks, Hio's talk and just Nimish's talk just before this. So I would like to start with the following celebrated conjecture of Raghunathan, proved by Ratner, that if you have a Lie group and you have a lattice in this Lie group, a discrete subgroup with finite co-volume, then we would like to understand orbits of every point under subgroups of G. Of course, this is hopeless if I took the subgroup to be, if I took G to be SL2R and the subgroup to be the diagonal group, then we know that this action is Bernoulli and there is no hope to understand for understanding every orbit. But the fundamental conjecture and fundamental theorem of Ratner says that the situation is drastically different if you assume your group is generated by unipotent elements. And unipotent elements are those elements that all the eigenvalue, all the complex eigenvalues are 1. So there is strong rigidity that we understand closure of every single orbit, and they're all proper submanifolds. So they are all actually orbits of intermediate subgroups. The example to have in mind, which is actually in some sense for application, number of theoretical applications, perhaps the case of main interest is G SLN R or its friends and gamma SLN Z or analogs in arithmetic setting. And the group W, a one parameter subgroup, which is obtained by exponentiating some nilpotent element. So this is, if you haven't thought about this type of question, this is just to have in mind. So you can take W to basically be 1, 1, 1, T 0, 0, or if you like more generic type elements, these two would do, and n equals 3. So these are the type of groups we are talking about. Now, prior to Ratner's work, important special cases of this in the context of Oppenheim conjecture were proved by Margulis and Danny Margulis using different methods. Ratner's proof went through measure classification, and then she used linearization techniques developed by Danny Margulis and also versions that she adapted herself to go from measures to orbit closure. But there was an approach actively being pursued by Margulis and Danny Margulis, which used purely topological arguments to prove this topological version. I'll come back to this later in the talk. And around the same time that Ratner's theorems were appeared, Nimish had also studied quotients of SON1 with lattices and unipotent flows here. This, I think, appeared in Hio's talk yesterday. She mentioned this work as well. So that's one remark I wanted to make. Well, this is not in, so what I've written here, historically, this should have been switched, but I just wanted to go in that direction. The case that is classical somehow is when W is a big subgroup of your group G. Think about G being SL2 and W being the strictly upper triangular group, or more generally, G being SLN-R and W being a full group of upper triangular groups. So these groups are called horospheric subgroup because they can be contracted to identity using some non-trivial element in your group, and they're all the elements that can be contracted. So they are somehow in the language of smooth dynamics, if you want, these are stable or unstable leaf for some flow, full stable or unstable leaf for some flow. And the study of this type of rigidity result for these groups has even a longer history. Already in the 30s, Hedlund understood what happens in dimension 2. So the picture is very explicit. If this is your copy of H2, which I've drawn in ball model, and the horosphere is a circle, which is tangent to the boundary, then when you project to your manifold, which is H2 mod gamma, okay, if the manifold is compact, then you have minimality. Every single orbit is going to be dense. If the manifold is not compact and you have a cusp, of course, you can't expect to have minimality because cusp, boundary of cusp is a closed horosphere, horocycle in this case. And but what Hedlund shows is that that's it. You're either closed or dense. And this picture is very, somehow very complete. Like I said, this is in sharp contrast with the case of geodesics. If you take a geodesic and project it, the only obstruction you have really is dimension. You can attain any Hausdorff dimension between 1 and 2 for the closure. So it's a very different story there. Now, I am going to be focusing on groups that are generated by unipotence or groups that are very close to groups being generated by unipotence, but it needs to be mentioned that cases of other groups, higher rank abelian groups, or random walks by non-amenable groups, as well as going beyond the homogeneous space and looking at maybe SL2R action on the space of on the modular space of compact Riemann surfaces. These have been extensively studied with fantastic results, and which have been celebrated by many awards, etc., etc. I don't want to. So if I were to list the names here, I think that would be the talk. Just list of people who have worked on these problems. But okay, so let me just leave it at that. And just going back to Hio's talk, the condition that gamma is a lattice is quite important in all of what I'm going to be discussing today. A natural question is how necessary it is. Of course, we saw yesterday that it is necessary. Nevertheless, there are classes of manifolds that this can be lifted, and this is also a fascinating direction that one would like to understand this type of rigidity result. And our knowledge is basically restricted to horospheric case, except the cases that Hio talked about. So that is maybe history of this part that I wanted to talk about. Like I said, I have left many names, left out many names, but my apologies. It's somehow, this area has been around for some, I don't know, 40 years or something, 50 years maybe now, and it's very difficult to just cover all the names in a half-hour talk. But the aspect that I want to somehow focus on is what's missing from these fantastic results. And what is missing is the quantitative aspect of the questions. Of course, if you want to look at the hierarchy of the results, one thing that I should have mentioned, but okay, now maybe I can mention, I emphasize that the somehow power of Ratner's theorem is that it gives you information about every orbit. If you were satisfied with information about almost every, in presence of ergodicity, this is a, well, you can call it a trivial exercise, using ergodic theorem or just using somehow second countability of the space to show that you have almost every point behaves the way you want it to. But Ratner's theorem gives you a statement about every point. And beyond uniquely ergodic systems, this is really the only example that we have information about every point. Of course, I mentioned these other works, but they are all Ratner type results that they give you information about every point. So now, Ratner went from almost every to every. The question I'm asking is that, okay, we have information about every, this is great, it's had many applications, but is it possible to somehow have finer information? Is it possible to have effective accounts on these density results. What's the rate that I'm going to fill up my closure? This is the question I want to ask. And this question was already, I'm not the first person to ask it. This question was already asked in Margoulis's 1990 Kyoto ICM talk, that he poses this question as one of the challenging directions to go forward. And I hope to somehow report on some of the progress that has happened around this problem in past 30 years or so. First, a word of caution is that usually such a result is going to be difficult to state, and it's going to depend on delicate properties of both your acting group and the point you started. Already you see this in for rotations on a circle. I've drawn a continuous example of this. If you want to take rotations on a circle, the angle, the irrationality of this angle enters the picture on how fast you will equidistribute on the circle. If you have a Diophantine angle, you will equidistribute fast. If you have something that is a Liouville number, you're very close to being approximated with rational numbers of bigger and bigger denominators, then it will take you forever to, will take me forever to become equidistributed in the circle. And here's a continuous example of this in two torus, because I said W was connected, just a connected example. This line is very close to the horizontal line, which has a periodic orbit. So if I think about epsilon as being very small, and I only go till half the time that this will reach height 1, what I see in the torus is that I'm only filling up half of the torus. So first, there are two things I want to mention about this example. Well, it tells you that if you're close to a periodic orbit, it will take a long time to be equidistributed, to be dense. Secondly, it tells you that you can't hope that the entire life happens near one closed orbit. You must allow families of closed orbits that maybe, so you spend some time near this, and then you go spend some time near the other one, but these come in some sort of a, if you want, tubes of these kind of subgroups. So these are the two things I want to mention about this. All right. So now, what is known? The case of when the ambient group itself is unipotent, so the case of the torus included, this was beautifully answered by Green and Tao, where they actually prove polynomial rates for equidistribution or density of these orbits, actually discrete times, even polynomial times they take. And but the methods there are somehow restricted to unipotent groups. They use induction, they use some van der Kolk trick argument. So they use induction on the nilpotency of the group to prove this. And there are techniques that just somehow they stop if you leave the unipotent word. The case that I'm going to be focusing on mainly is what happens for semi-simple groups. So that is the case that is going to be the main concern here. Again, these results I'm stating are not in chronological order. I've just listed them in an order that I hope will make the talk easier to follow. So Lindenstrauss and Margulis proved an effective version of the Oppenheim conjecture in dimension 3. And what they show is that so Oppenheim conjecture says that if I give you a ternary form, ternary quadratic form, non-degenerate and irrational, not being a multiple of a rational form, then for every epsilon you give me, I can find you an integral solution. I can find you some vector in Z3 so that the value of the quadratic form is less than epsilon. So the natural question is, how big of a vector do I need? I already know that for indefinite rational forms, Kessel had these bounds on the size of the smallest solution you have. This is for irrational. And what they prove is this beautiful result that if you assume your form is Diophantine, think about a form that's not a multiple of a rational form, but one of the coefficients is square root of 2, that type of form. Then for every epsilon, you can find the solution, and the solution has a bound. So the size of the solution is exponential of 1 over epsilon to power n. N is an absolute constant. So there's an absolute constant that for a Diophantine point you give me, I can solve this Diophantine inequality like this, provided that epsilon is small enough, and this, how small this initial epsilon should be, this depends on the Diophantine properties of your point, the degree of the coefficients, etc. Okay, so this is one beautiful result. As you see, we don't quite get the rate that maybe now we know actually for a typical form. For a typical form, you are going to have a polynomial rate. This was, well, at least I know of two works that they will give this, Atria and Margulis, and works of Dubey, Kelmer, and Anish Ghosh, that you will get a polynomial rate for a typical form. Also, Bourgain showed that for typical form in a one-dimensional family of quadratic form, in a certain one-dimensional family, you get a polynomial rate. But what one gets here is this type of exponent of a polynomial. And this work somehow so builds on this topological approach of DAE and Margulis that I mentioned. That topological approach utilized a notion of minimal sets. Of course, minimal sets are not effective, but there's an effective replacement by this, which is this linearization technique of DAE and Margulis. And that is somehow what is done here. If you just do that, the rate you're going to get here is going to be worse than this. You're going to have x pub this. Another ingredient, another novel ingredient in this work is some combinatorial lemma, which actually takes care of one exponent, and you get this. In an ongoing joint work with Strauss, Margulis, and Shah, we prove actually a full-blown effective version for unipotent flows on arithmetic quotient. The rates we get are quite bad. If this is one exponent here, imagine that you're going to have x pub 1 over epsilon n, and the number of x's you need depends on the dimension. So the higher the dimension, the slower the rate of equidistribution. But given the current technology, I mean, with the current technology and in this generality, this seems to be somehow what one can do without introducing new somehow techniques. If you want to take DAE Margulis's proof and try to effectivize it, this is a tedious work. It's challenging, and what you're going to get is a rate of this sort. It somehow doesn't seem possible that just effectivizing existing proofs will give you better rates. Okay. Now, I want to talk about whether we know better rates in semi-simple settings. As I already mentioned, Green and Tao proved polynomially effective density result in the case of unipotent groups. Now, how about in the case of semi-simple groups? Some results are known. The action of horospheric groups, which I mentioned, were classical in the qualitative world, works of Hedlund, DAE, and Furstenberg. In this case, also, they are very well understood. They are well adapted to techniques from harmonic analysis, decay of matrix coefficients, mixing rates, whatever you want to call it. Different people have strong opinion on how to call these techniques, and there is extensive literature on this. This is again just some list of people who have worked on this. Margulis's thesis, Sarnak's, what I thought was Sarnak's thesis, but I may be wrong here. Berger's work and several other works, they address this case of horospherical group. There is an asterisk there for Strombergson's work. Strombergson has certainly worked on the horospherical group case and has probably the sharpest results one has, but another theorem of Strombergson's which needs to be mentioned is the case of semi-direct product. He's also proved the result about SL2R semi-direct R2 and the acting group being the the one that projects into horospheric in SL2. And this is, okay, this is beyond horospheric case. It's closely related to horospheric, but it's beyond horospheric case. And these works here are related to translations of symmetric groups. These also, many people have worked on in this direction as well. These symmetric groups are somehow, because of polar decomposition, and it was about decomposition, they're close to horospheric groups. So algebra helps there. And one can show that if you translate these in a direction that you increase the volume, you have effective results. A fundamental contribution was made by Einzidler, Margulis, and Venkatesh. This is, I think, maybe 2007, 2008, where they study periodic orbits of semi-simple groups in quotients by arithmetic groups. And they prove a polynomially effective equidistribution. It's polynomial in the volume of the orbit. And somehow you need some conditions on these groups, okay? No compact factors, and somehow the group that you are acting with is fixed in this original work. We were able to, in a follow-up work, lift some of these conditions. The new ingredients that were needed were, this is the conference at Tata, so were Prasad's volume formula and the fundamental work of Borel-Prasad that went to removing some of these conditions. But there is a reason that one gets a polynomial rate here, and the reason is this strong, deep input from number theory, that of uniform spectral gap. That when you look at all these periodic orbits, there are congruence quotients, and then you have property tau. So you have a uniform spectral gap, which you can use to get an effective ergodic theorem. And when you have an effective ergodic theorem, then you can somehow try to build on it. An important direction that is remaining in here is to allow for the acting group to have centralizers. This will have applications in number theory, which, okay, that seems to be quite technical and still remaining open. That is in there. There is very important work, especially for what is going to follow. This work is important on its own, but it's also, it's even more important for the remainder of this talk, is the work of Borgan, Furman, Lunen-Strauss, and Moses, where they study random walks on torus, and they get effective equidistribution results here. The techniques there are quite different from the techniques I mentioned here. They use some projection theorems of Borgan and theory of random matrices. And well, because it's a torus, they also use Fourier analysis, but the techniques are quite important for what is to follow. Okay, so this is some brief list of polynomial rates that are known in the context of homogeneous dynamics, or at least the polynomial bounds I know of in the context of homogeneous dynamics. People should correct me if I have left out something. So as you see, non-periodic orbits of subgroups which are not horospheric, we don't have any polynomial estimates yet. So the case I mentioned, the joint work with Lunen-Strauss, Margulis, and Shah is about general orbits, but the rates we get are far from polynomial. The rates you get are rather weak. So I want to concentrate on this very explicit example. You can take either one of these two groups, whichever you like. So SL2C or SL2 times SL2, and gamma is a lattice. And I want to fix a copy of SL2R, inside G. Of course, in SL2C, it's clear what I mean by a copy of SL2R. In SL2 times SL2, there are 3 copies, but 2 of them are normal. So you can imagine that I'm not interested in those. Study of those reduces to horospheric cases. That is not very interesting. The interesting case is the case of a maximal subgroup, which is this diagonally embedded copy of SL2R. And I'm going to fix the Borel subgroup, the upper triangular subgroup in H. Of course, you can complain that I said groups are generated by unipotents, and this one is not, but this is very closely related. We already saw what Nimish was discussing was these expanding translates of horospheres. So it's this is of that case, and maybe more using more algebraic terms. This is an epimorphic group in H, and already I think in early 90s, Shachar observed that if you have an epimorphic group, orbits of epimorphic groups so orbits of P are the same as orbits of H using Ratner's theorem. So it's very closely related to H. Indeed, H is non-amenable, and if you want to understand orbits of H, you better work with an amenable subgroup of it. It's somehow you're just forced to do that, because if you fix a ball in H and you move this ball with the random elements, this is going to go in the direction of P. There's just nothing you can do. So one way or another, you need to study this P action. And the theorem I want to discuss is the following joint work with Elon Linder-Strauss, that if you assume gamma is arithmetic, and I will come back to this, then we have a polynomial density result. What is this saying? Okay, it's a mouthful to read. Like I said, and we already saw for a rational rotation of a circle, it could be that I'm stuck near a small rational subspace. So case 2 you see here is being near small rational subspace. Case 1 is the interesting case, which is density. So what this is saying is that you give me a point, and I want to apply ball of radius r in P, in the group of upper triangular matrices, to this point. And I want to ask whether this is polynomially dense, whether I get r to power minus epsilon close to every point. The statement is that yes, unless you're too close to small orbit of the SL2 that I discussed. So you're either polynomially dense, or there's an obstruction, and the obstruction is explicit and algebraic. It's a small volume orbit of the group H. That's what the theorem says. Now maybe we can go through it and try to see what the parameters are. So this, you give me delta. Delta is supposed to say what complexity of rational points you're allowing me. You give me x0 and you give me t, which is large. Now, either I'm dense. Of course, x is not compact. I can't hope to be dense in all of x. I need to cut some big compact part of x, and this is what that is. If x is compact, you can just put x to be this to be all of x. When x is not compact, I cut out the cost at a certain height. So either I come within t to power minus epsilon of every point in this thick part, or I am close. I'm very close to a small periodic orbit of H. So that's what the theorem says. Okay. So the proof uses ideas from additive combinatorics, broadly speaking. So we use some tools from incident geometry, and we use extensively Margulis functions in our arguments. There is, so I'm not sure I'll have time to get to the maybe slightly more in-depth discussion of the proof, but the proof will have 3 stages. So the stage 1 is some initial randomness, which we get using arithmeticity. I should mention here that I said I was going to mention a word about arithmeticity, but I somehow didn't. If you don't take the group gamma to be arithmetic, you need to modify the statement. Rather than being near a periodic orbit, you should replace this by you're near a point which has large stabilizer. So it has a stabilizer which is non-elementary, and it's which is non-elementary. And inside the stabilizer, I can find the small elements. That's somehow the payoff for arithmeticity. But anyway, we use arithmeticity to get some initial randomness. then we need to, this gives some small dimension. You need to bring this dimension to a dimension that is useful for spectral purposes, and that's where we use Margulis function. There's a bootstrapping step where we use Margulis functions, and then in the end we use decay of correlations in the space X to conclude. Hopefully, if there is time, I will we will see these slides about this. But so I said the main point of this project was to prove something about non-periodic orbits, but the methods apply to periodic orbits also. And the advantage they have is that for periodic orbits, you don't need arithmeticity. Periodic orbits, they are somehow arithmetic by nature because two rational points can't get close to each other. Two periodic orbits can't get too close to each other. There are different ways of seeing this, but maybe the one elegant way to see this is using, again, Margulis functions. This is an argument due to Margulis that shows that periodic orbits cannot get close to each other without assuming arithmeticity. Okay, so it applies to periodic orbits also, and the bounds we get are rather, so they depend on rather weak properties, coarse properties of your space. The mixing rate, the volume, and injectivity radius of the core. And what good does this do for us? Because we all heard David Fisher's talk yesterday that somehow in all these examples I'm discussing, either you are arithmetic or there's only finitely many closed orbits. So it's a theorem about finitely many closed orbits, but it can also help to give a bound on how many, at least in some cases. And this is this application I want to mention, and then maybe, I know I'm going over my time with a minute or so, but I'll mention this application and then stop. So these examples appeared yesterday in David's talk, that you have these hybrid manifolds constructed by Gromov and Piatetsky-Shapiro. You have 2 3 manifolds, both of them arithmetic, but non-commensurable. And you have some surface, which is the same surface in both of them, in a sense. So you have submanifolds of M1 and M2, and these have boundaries which are isomorphic to each other. And these submanifolds have Zariski dense fundamental groups, this submanifold with boundary. Then I can cut open M1, I can cut open M2. These examples appeared in Hugo's talk also. These manifolds with Fuchsian ends are what you get when you cut this open and don't close it. You just let it become a flare. Then you can cut it open and glue them together. You get a new arithmetic 3 manifold. Okay? And as David mentioned, so this is a more detailed discussion of how to construct this. Let me skip that. As David mentioned, it was proved by Fisher, Lafond, Miller, and Stover that there's only finitely many periodic orbits in here. This goes through an angle rigidity result, which was proved by them and independently by Benoit and al., which says if you have a closed orbit, it needs to intersect this surface in the middle in an orthogonal angle. So it needs to be perpendicular. Using this and our effective density, we can say how many periodic orbits you can have. As you see, the number is polynomial in terms of the geometry of your 3 manifolds. So maybe I'll stop there. I am sorry to have gone over time.
Not at all. So let's thank Amir for the really lovely talk. That was fantastic. Are there any questions for
It's not a question. I want to apologize to Amir for the disturbance caused at the beginning of his lecture because I'd forgotten to unmute. I'd forgotten to mute my mic. Sorry about it. And thank you for your very nice talk.
Thank you. Thank you very much.
Any other questions? So Amir, I just had a small confusion. So this result of yours and the previous Einsiedler, Margulis, Venkatesh. So what were the groups and the things? I just got confused.
Oh yeah, so the group, you have a semi-simple group.
Yeah.
You have a semi-simple group, and then you have a semi-simple subgroup of it.
Oh, I see. I
And
understand. I see.
Yeah, yeah,
This
yeah.
good, man.
But
All
it's somehow this second result is in a Delic setting, and
Yes.
there is no splitting condition. Somehow that is the
Yeah. Okay. Any other questions or comments? If not, let's thank Amir once more for a lovely talk.
Thank you.
Okay, so I guess my job is now over. I'll hand over to Professor Dani.
So with the end of the last session, the final thing in the conference is the valedictory function, and as we have indicated, it's going to feature felicitation for Professor Raghunathan, which I'm sure many of you are waiting. Let's take the sort of standard 10-minute break and reassemble at 8:35, and then we will start the session. I request the technical committee people to make this announcement on the screen also if possible. So see you all at 8:35.
Danny.
Yes, yeah, hello.
Okay, so when I am supposed to talk?
I think you will come second. I'm first going to have somebody, and then I'll show in about 8:40 or something. I think 8:40, 8:45, something like that. So around 8:40 from our time. So from about in about 15 minutes from here. From now, yeah.
Hello, Balu.
Hi. Yes, sir. Yes.
Hello, Balu.
Yes. Hi.
Hi, Ramdas.
Hi. Rather, you managed to cut your hair for the occasion.
No, it's the, what do you call it? It's this.
Headphones.
I forget what you call it.
Headphones.
Which conceals my. Anyway, I don't have much hair in front, in any case. It's only at the back, and this enables me to conceal it. The headphone.
Hi, Ramdas. Hi, Balu.
One should say halabalo.
Hi, Kaushik.
Hi there. Suri.
Hi, Kaushik. Hi, how are you?
I'm very good. As they say in America, I'm very good. Fine.
Hello, Raman. How are you?
Good. How are you?
Oh, good. Thank you.
Raman. Hi. How are you? Yeah. Raghunathan, many happy returns of the day.
Thank you. Thank you.
Hello, Dani here. Yeah, no, I just wanted to confirm. So when someone is speaking, the image can be pinned, right? So that is to be done individually or it can be done centrally. No. Say after this we have the felicitation. So at that, I mean, right now we are seeing, I don't know how the pinned image comes sometimes. That seems arbitrary. So I just wanted to know when we have this felicitation function, various people will be speaking individually. So
Mute. Okay. Right. Mute. Okay.
But in Zoom, we will be in Zoom, right?
Dani, if you are a host, you can.
Yeah, so that has to be changed.
Spotlighting. You can do something called spotlighting this particular person.
So you can
have to find out how to do that. Any host can do that. Or if you have a technical person who is a co-host, that person can do that.
But actually, I asked him, and he said it should be done individually. So maybe we'll just simply make an announcement so that people know. I thought it should be possible to do it centrally,
but so if you choose speaker in the view option, then the person who is talking will be on the whole screen.
Yeah.
But that is done individually, right?
Yeah, but you do, everybody does it, then I mean it remains like that.
So let me spotlight someone. Like now, does everyone see Professor Dani?
Yes.
Okay. All right. Then it is working.
Yeah.
Okay.
Hi, Regina. Okay, she's disappeared. She was there on the big screen for a while.
I am here.
Ah, there you are.
Yeah, it's just that now Dani is spotlighted, so you can't see him. So.
Yeah.
Correct.
Hello, Kaushik.
Hello, Riddhi.
How are you?
Hi, Ramanan.
Hi. I should tell Raman that it is not birthday anymore, it's birth night now. Yeah.
No, I don't know. I'm told I was born at 9:30 in the evening. So.
Stop. Hi, Kausik.
Hi. Good. So, another occasion to see everybody's face on the screen.
You have doubled yourself.
Yeah, recent past, COVID is responsible.
No, I'm saying there are two pictures of yours.
I thought you meant my size.
No, we don't see you double the size. We know means maybe you should go up on the sit. Even then, no. No, the photograph doesn't show it. No,
Yeah.
it doesn't.
No, he's not. He's normal self.
Yeah.
The daily fluctuations don't show.
Post.
Yeah, it is 8:35 as the announced time. Welcome everyone for this last session of the conference, which will to serve as the validatory function as well as the felicitation for Professor Raghunathan. The day before yesterday, when I was to start, I had a great deal of apprehensions and sort of running anxious about it. But I find that a lot of things have, most of the things have gone well, except for one speaker not being able to turn up. Everything has gone according to the plan, and it has been a very pleasant experience. The kind of warmth that was expressed by many speakers, apart from the technical, apart from the mathematical content and everything, the warmth that was expressed by the speakers and the participants, the participation, degree of participation, etc., has been quite satisfying. And the role of Raghunathan as the sort of master of ceremony has been all over the place, visible in many contexts. One of the very exhilarating things that I found was the participation of Raghunathan himself. I mean, practically all the time, his video and everything was on. He could be there, including when there's some kind of disturbance, etc. But the expression on his face, it was clear that he was sort of really into it, and the questions and so on. And then he, in fact, in one of the messages he wrote to me, that it has, the conference has been morale booster for him. It's a very happy thing to hear from him. And surely I believe we will have a lot more things to come from Raghunathan. And this is 80th, and then maybe we'll look for another occasion, maybe 90th or even before, and so on. And a lot of people have worked for this conference, where we have seen the scientific committee, technical committee, and so on. And for the smooth running of the event, there's been a lot of effort has gone into. The names are out there on the website, and I'll not go individually into the names on this occasion. The main, so I'll express my thanks to all the speakers in the first place, the participants, and the members behind the scene, in the committee, the scientific committee, who advised us on the speakers. Then the organizing committee, which set up various programs. I hope all of you have had a chance to look at some of the things that have been put up on the website, including the interview that a group of young mathematicians had with Raghunathan, and which again shows the energetic and inspirational role that Raghunathan would still continues to have. There are also some articles, including my own, but I do hope that, and there is also a group photo which shows a lot of people in the participation, etc. So I thank all the people involved in making this possible. And now we are going to felicitate Raghunathan by recalling the reminiscences of people that I forgot to mention. Of course, this was mentioned at the inauguration. There's a souvenir which has a collection of reminiscences from various people, and this was announced, and hopefully you had a chance to have a look at it. But there are many more people here who would like to say things, and some of the people who have written in the things would also like to say something in person, which has a different charm naturally. So I have invited, or I have confirmed that some of the people would be saying something. So initially we will have the list as I have made it, and then we will have other people wanting to come up, and it would be convenient if interested persons could send a direct message chat to me, so that I can make a note and invite the person suitably at a suitable slot. In this respect, I'd like to begin with one of the people who has known him. I think he's the person from here who has known him the longest, and I'm sure many of you recognize that it is Professor Ramanan. With that, I first invite Professor Ramanan to say a few words on this occasion.
Oh, thank you, Dhani. See, apart from the 80th birthday of Raghunathan, this is also an occasion on which I can celebrate 60 years of friendship with him. So probably I am the only one who can claim this honor. And in one's career, one meets and discusses mathematics with a lot of distinguished mathematicians from all over the world. Nevertheless, I would say, pardon?
Yeah, please go ahead.
Yeah. So, nevertheless, I would like to say that one of the fastest thinking mathematician whom I have met is Raghunathan. And what is more, he is used to parallel thinking. So you discuss something with him, you are discussing, and then you see that it hits somewhere, and then you do not know what to say next. Then he suddenly says something from an entirely different point of view, and his brain has been thinking on two parallel lines all the time. And it is not as if he starts somewhere, it is somewhere in the middle. So I have had this experience a few times. And once also, while he was giving a lecture, he was thinking on some lines. Then I very, hesitatingly said, this is also, you can also look at it this way or something like this. And I thought it will take some time for him to grasp that. No, the next sentence he says, yes, that's a differential geometric idea. And then he began explaining my idea. He gave up what he was saying and then started saying something. He says, this is a differential geometric. This is the way, that's what Ramanan is saying. So this kind of immediate grasp of something, I have hardly ever seen in any other mathematician whom I have met. And it has been a great pleasure all these years to have been his colleague and to have also initially to have taught him a few things and later learned a few things from him. And however, I have never collaborated with him. That's because his subject was somewhat different from what I was interested in. So I wish him a very happy and productive and continuous administratively he has been very useful, and he has been doing tremendous service for mathematics in India, and I wish him all success in all he's saying, and continuously he should be healthy and continue to do whatever he has been doing. Wish you all the best, Raghunathan.
Thank you.
You're muted, Professor Dani.
Dani, you are muted.
Yeah, thank you, Ramanan, for the reminiscences from one of the earliest people who has to have known him. I'd next like to invite Professor Margulis, with whom there is a very complex relationship. Had a long relationship that Raghunathan has had at the academic levels, and so Professor Margulis.
Okay, so let me start first. Congratulations to Raghunathan and on his 80th birthday. So it's a great anniversary. So let me start with some story which I told probably several times already. So it's in 1979, I visited Bonn on the invitation of Hirzebruch from the beginning of July until the beginning of October, and probably in September I met Gopal Prasad, and he mentioned the. So do you hear me?
Yes, yes.
Yeah, and so met Gopal Prasad, and he mentioned the conjecture of Raghunathan about unipotent flows, and even probably more importantly that the connection of this conjecture to the statement about quadratic forms, which at that time Raghunathan probably mistakenly quoted Davenport conjecture. Now it's again actually before that and after that it's Oppenheim conjecture. And somehow I was very intrigued by then, and probably and started to think about that from maybe some interruptions, and probably in the mid-80s I was able to prove not the entire Raghunathan's conjecture, but some necessary special cases. It's about orbits of bounded orbits of orthogonal groups, SO1 and SO3 SO3 Z. And after that, I somehow became very much involved in homogeneous dynamics, and somehow it was still probably interested in that. So it's for several decades. So I probably, so it somehow it has big influence on me. So I probably first time when I met Raghunathan was in 1988. It was probably again in during my another visit to Bonn. I think Raghunathan and Daniel also were there. And then I visited Tata Institute several times, and then maybe every 3 or 4 years I met Raghunathan in different locations. So initially it was very difficult for me to understand Raghunathan for 2 reasons. So there is a number one, that Raghunathan speaks very fast. And there is a number two, that probably my linguistic skills in English were not good enough. So now I understand Raghunathan probably quite well, and so he still speaks very fast. Probably my skills in English improved. So it's, yeah, with Raghunathan we worked on, from time to time, on similar problems, and we never wrote a joint paper, but certainly we influenced each other. And I want to emphasize that I consider Raghunathan as one of the main influences, and I want to add that probably without his influence, my mathematical life would be quite different. So congratulations again, Raghunathan.
You have to unmute yourself, Professor Dani.
Thank you, Margulis, for that quite detailed and somewhat rather emotional expression of your reminiscences. Let me next invite Alex Lubotsky, Professor Alex Lubotsky, who is also quite closely associated with Raghunathan.
Thank you very much. It's a pleasure to be here. It could be even more pleasure if we could have it in India. Anyway, thinking back, this gives an opportunity to go back. Then I knew the name Raghunathan already as a young student. He was already a very world famous mathematician at that time, and his book on discrete subgroups of Lie groups was the Bible for people who got into that field, which just started to be very, very popular at the time. So I was very excited when some years after that, which I cannot really remember in what year exactly it was, but something like 40 years ago or 35 years ago, I met him, I think, for the first time at Yale University. Now I have to admit today that the first meetings with him were not so easy, and in fact, even a little bit frustrated. Because, as Margulis said, Raghunathan speaks very fast, but for me, this was not the only, maybe for Margulis, this was the only problem. For me, there was another problem, that he thinks very fast, and he knows everything. And Raghunathan is one of those who can move from number theory to group theory to dynamic to ergodic theory to geometry, and he understands everything, he knows everything. And when you talk with him, you really feel so stupid. So I have to say that I was very frustrated. He was very generous. He was extremely kind. But at that time, I remember I thought maybe I should leave the profession, or at least move to another field. I remember that I little bit calmed down when Mosto told me that also for him, Raghunathan speaks and thinks too fast. So I said, okay, maybe I can survive with these high standards. And I was even further excited when a few years after that, we began to work on together some problem about U elements, and eventually about the Gromov-Kashdan conjecture, together also with Shachar Moses. I remember that the starting point for that work was in a conference which we met. Now I don't remember where exactly, but maybe Raghunathan, you will remember. I tell you why. Because you had to go at one of the days of the conference to the, I'm pretty sure I remember, to the Canadian consulate. You wanted to get a visa there to visit your sister or some relatives of yours. Do I remember correctly? And then I decided that rather than listening to the lectures, I will join you to the consulate. I was sure at the time that I will learn more talking with you on the way, and then listen to the lecture. So in fact, we went there, and there was a long line. We have to spend there a few hours. Usually I don't have patience for staying on lines, but this was the most pleasant staying online in my life, because I learned from you so much. And this was really, that was the starting point of our project. And maybe we should dedicate the paper to the Canadian bureaucracy that enable us to make a progress during that conference. And I learned for you during this work and over the years so many things in mathematics. So I'm really so grateful for you. But I really want to mention something outside of mathematics, which really, Raghunathan, for you and for me, you are a role model. In a kind of a personal way, I look with a lot of interest in you and your family and your wife. Somehow you are facing, I feel, the same kind of problems that I face in my life. The combination of being loyal to an old tradition and at the same time emerging in the modernity. You know, you are very Indian in your culture, in your loyalty to the tradition, and at the same time you are at the top of the world in the scientific world, and you know, you are very modern and very old-fashioned at the same time. And I have to admit that I tried in my Jewish life to do exactly the same thing. So I feel and I understand the difficulty, the struggle, the dilemmas, and you are and I watch you and compare your life with a lot of interest and admiration. And another point of admiration that I have to you, which I also try to imitate, is your loyalty to your own country. There is no question that you could get a fancy position in any place in the world, you know, with a lot of money and fame, etc. But you decided to be loyal to your own country and work very intensively to develop its mathematics and its science. And also in this aspect, I try to follow your footsteps. So you are really a role model for me in more than one way. And I want to take this opportunity to say thank you, big thank you for all that. And I just hope that I was in your 60th birthday in India. I was in your 70th birthday conference in India. I hope that I will come to your 19th birthday and 100th birthday, 110, and 120, which is the... Thank you very much, and thank you all for having this.
Thank you, Alex. May I next invite Professor... May I next invite Professor Gopal Prasad? Gopal Prasad?
Myself.
Not here?
Hello, I am there.
Yeah, okay.
Can you hear me?
Yes.
Can you hear me?
Yes.
Very good. So this is Gopal Prasad, though my name is written Medha Prasad, which is my granddaughter, and I am with her. So I would like to begin by saying that it's a great pleasure to be here to celebrate Raghunathan's 80th birthday together with Raghunathan and Rama and all of you. I wanted to share with you some personal and professional reminiscences because I was one of the first students of his at TIFR. I joined TIFR in 1966. Raghunathan was in the US at that time. When he returned in 1967, he gave a set of rapid courses on Lie algebras, on differentiable manifolds, and on the initial chapters of Hirzebuk's book on new topological methods with a proof of de Rham's theorem given there. TIFR math then was a very small community, about 40 people, including professors and students. Not many will know that Raghunathan was very interested in topology then, which was seeing rapid growth at that time. With his infectious enthusiasm, he got me interested in that field and suggested a problem on flat bundles for me to work on. In the same year, Mosto was scheduled to visit TIFR, and I was asked to prepare to write his lecture notes. I learned everything I could about Lie groups from the books of Chevalier and Hochschild. I remember with fond memory that Ramnan gave me and Parthasarthi a very rapid introduction to compact Lie groups at that time. The course Mosto gave on his proof of rigidity in rank 1 case was very much above my level. I barely managed to write notes on it. Raghunathan afterwards gave a detailed and a very interesting course on discrete subgroups of Lie groups, an expanded version of his course at Yale, which he turned into a very popular and well-referenced book. This course changed my direction from topology to discrete subgroups of Lie groups. Mosto submitted a short paper for publication in the Journal of Indian Math Society, and Raghunathan gave it to me to read, a generalization of the result from non-uniform to from uniform to non-uniform lattices immediately arose, and Raghunathan enthusiastically got involved and contributed many important ideas. This became the first of a very long and productive collaboration with him. The first work also led to an invitation from Mosto to me to visit Yale. This visit turned out to be very fruitful and consequential for my family. When I returned to India in 1974, after time at Yale and Princeton, I read Raghunathan's first paper on the congruent subgroup problem and became interested in that field. We collaborated on the cohomological aspects of that problem for several years. And I learned a lot from him at that time. In fact, whatever mathematics I know, I learned mostly at TIFR from him. So I'm really very grateful to him for all that he did for me at that time. Raghunathan's personal characteristics that I found wonderful during these very early collaborations were his enthusiasm and warm encouragement. Whenever I wrote papers, whether with him or independently, he was enthusiastic and encouraging of the efforts. He was also very approachable. Indeed, he would generally drop into my office, and these visits would become extended mathematical conversation lasting several hours. It's a great pleasure to thank him. And also I would like to mention Rama. She has been always very kind to me and Indu, and very supportive during many periods of my life. Our visits to Russia and Minsk was quite memorable, and I don't have time now to mention all that, but I'm really very, very grateful to both of them, and I wish both of them a very happy and healthy life together. Thank you.
Thank you, Gopal Prasad, for the reminiscences from the young days as a student, as the first student. So it should be interesting. Let me next invite Balasubramanian, who is involved with Raghunathan in a somewhat different capacities, and let him tell us about it.
Okay, let me start thanking the organizers for this opportunity to say a few words about Professor Raghunathan. I joined Tata Institute in 1972. Am I audible?
Yeah,
Yes. Yeah.
I joined Tata Institute in 1972, and he has been like a mentor to me from my early days in TIFR. Not only Professor Raghunathan is a great mathematician, but he's a great teacher too, as Professor Gopal Prasad just pointed out. He has an intense passion to interact and to educate the youngsters. And I think that is probably what attracted me first to him, because he would be spending most of the time in the canteen with the youngsters discussing mathematics. He has also been spending hours to promote a mathematical culture in this subcontinent. He has been a member of NBHM from its inception, and then later became a chairman. As Professor Dhani pointed out in an article in Frontline, the various activities of the board have made a substantial difference to mathematics in this country, and Raghunathan's stewardship has been crucial to its success. He also realized that having some mega events would give an impetus to his dream of developing the level of mathematics in the country. Particular mention should be made about Srinivasa Ramanujan Bicentenary Conference in 1987 in Chennai, International Congress of Mathematicians in 2010 in Hyderabad, and Ramanujan 125 2012 along with the Delhi University. Out of all these mega projects, I am mentioning these three, because in these projects, I could see him from close quarters because I was also a member of the committee which he constituted. I would see him from close quarters, overawed by his administrative skills and his management, and taking decisions almost immediately when the need arises. I just give a couple of examples. The Bicentenary Conference, Raghunathan was very desirous of inviting all the college students because he thought that it would be a good motivation for them. However, since the program was to be presided by a dignitary and the protocol demanded that the list of the attendees to this conference be given to the police at least 2 days in advance. And that is not possible, essentially because you don't even know who are the people who would be coming. And similarly at ICM, Raghunathan had some ideas to request of Hyderabad University to give an honorary doctorate to a few, and there was a last-minute hit. And these are problems that have demanded action then and there. I could learn a lot about how this administration, how to take decisions, and how to arrange the meetings, etc., by just watching them. As most of you would have known, the National Center for Mathematics is the brainchild of both TIFR and IIT Bombay. And Professor Raghunathan was the first head, and I was also involved. And that was definitely a very good learning experience for me. And I was surprised at the end of the first term, he asked me whether I would take over. I was hesitant since any comparison between the successor and the predecessor would always make me a loser. But anyway, Raghunathan has decided that I would be the successor, and that settled the matter. And as Professor Gopal Prasad also pointed out, I could clearly imagine with Raghunathan spending all the time in his research, teaching, and promotion of mathematics, how much of a sacrifice Rama would have done so as to allow MSR to freely pursue his dreams. Really hats off you to Rama. I pray God to give you a long, healthy, active life to Raghunathan so that the students of the new generation can learn and interact with this great mind.
Thank you, Balasubramanian. Let me next invite Nimish, one of the later students. Nimish Shah is here.
Professor Raghunathan has been a great source of inspiration for me all through my career as a mathematician, starting from being a graduate student. Going to Tata Institute, he was one of the first people with whom we got connected, all the young people. He would come to office of the new graduate students very regularly, chat with us, have tea with us, and somehow he created so much enthusiasm, and he could rub his love for mathematics to all of us, that we felt that doing mathematics was the best thing best thing we have chosen in our life, and Tata Institute is the best place to do mathematics. We never felt because of him somehow created such an atmosphere that it never felt that it was not it was in India or in there are less number of people. No, it was just it's like you felt that it was being in Princeton just because of him. And I've been fortunate to have a long association with him as a student, and I was also very fortunate to have Gopal Prasad and Dani as my advisors, and they played also a very important role in my mathematical career. Another thing I found about Professor Raghunathan was that even after Ratner's proved the conjectures, he still wanted to, he had his own way of thinking about this problem. He had his own idea how it could have been proved using some ideas using representation theory and Langland's some constructions and his theorems. He kept on trying this problem for a very long time, and many times he came up with solutions. And as Professor Ramanan said, I would listen to the solution, and my test case was that if you can prove it for a horocycle, one-dimensional horocycle for SL2C mod gamma, if your proof works, then it is very worthy of something. So he would explain, I will try to check that proof in that case, and then find some mistake, go back to him. Instantly, he would come up with completely different idea of handling it. I wonder, you show him some flaw somewhere here, you try to repair it. No, nothing. He just give a completely different idea and completely different proof. Again, he will try, and in few days he will come up with another proof. I saw that happening over a 6 months period, again and again, and nothing stopped him. Anything roadblock, he would find another way. And not that he finally gave a new proof, but I could see how he thought about mathematics just completely naively, in a very different kind of ideas, and nothing bothered him. He would always find a way of doing something. That was amazing. And one more thing I want to say is that Raghunathan and Rama, especially because of Rama, she just gave a big surprise to us on our day of marriage. They just came to Ahmedabad, and I didn't know about it. I just invited them, but didn't expect they would go. But they came, and it was such a surprise and pleasure that we always cherish that. And Raghunathan and Rama both made our stay in TIFR just like it became a family. Thank you very much for your all kindness, and we both of us wish very happy birthday and a long, very productive life together. Shatam Jiva Sharadam.
Happy birthday, Professor Raghunathan. Once again, thank you very much, Rama and Professor Raghunathan, for involving us in your life. We are very, very thankful to have you both in our life. Happy birthday.
Thank you, Nimish and Shilpa. I have one more student of Raghunathan in the list, and it's Rajan. May I invite Rajan?
Yeah, thanks for inviting me. And of course, first of all, my thanks to Raghunathan for teaching me all the mathematics I knew for a long time. I learned a lot of mathematics, and it was a great pleasure. Of course, there are many things I can repeat. His indefatigable energy, his enthusiasm, and many things. So I just want to say something. I don't, of course, I have great regard for for him from all those angles. But one thing which struck me in my student days and later was that I felt that how single-handedly he kind of built this school of Lie groups in TIFR. We are of course completely isolated, and there are these various theories going on, but so the algebraic geometry at least had a fair number of people who are involved in it. But in some sense, I think it was Raghunathan who built completely this this subject of Lie groups, discrete subgroups, the action on G mod gamma, in the homogeneous spaces and other things. And I felt one way was that I think he straight away went for the central difficult problems. And this was always there for him. It was never a question of warming up, with a smaller problem or trying to look at this, and you get ahead, you learn the subject, and then you go ahead and look at a difficult problem or whatever it is, central problem. But Raghunathan always had looks at very difficult central problems, which of course being central and difficult, they were pretty difficult. And of course, for him it did not matter. He was never, as Nimish just said, in something, nothing defeated him. He just bounced back after anything. But for a student, it could have been, it can be very difficult if you don't make progress and you feel very defeated after that. But on the other hand, what you realize later is that in the process, you learn a lot of very good mathematics, and you're exposed to a tremendous amount of mathematics, which stands you in good stead for the rest of your life. So thanks to this thing, but he also says that you have to look at very good problems, which was very, very useful. The way Raghunathan did, of course, apart from looking at the central problems, the way he built this was to lecture. And I think, as people have mentioned, and I got to know even before I joined Tata Institute that you can expect a course of lectures from Raghunathan almost every year, and it was true. And so this was, as soon as I joined, he had a course of lectures on discrete subgroups of Lie groups. That was in '84. I used to just attend those classes, and then later on, there are so many courses which were there. He, as a student, he encouraged me also, if I had to learn some things, not to lecture to him in private. He would just say, "Come, he would announce a course of lectures, so that makes you prepare better," or whatever it is. And you have to lecture for an open audience. So this was always the case. If I wanted to learn anything during my student days with him, it had to be public lectures which I had to give, a seminar which had to be run. So I lectured on theta functions and for the cohomology, and then later on, the work of Bunsen, Zelewski, and many other things. So it was always he asked us to lecture, and it was very good. And the other aspect I felt was that at many points of time, he has this, he places an emphasis on scholarship. Of course, he had this great enthusiasm for topology. Whenever, you mentioned the name Tom, his eyes light up, and is probably the mathematician who inspired him the maximum. And he's immediately, whether he's repeating it for the 100th time, it's the same enthusiasm and energy with which he was repeating those topics. But again, although I feel that for him, the scholarship was in pursuit of research, but it was not scholarship per se for scholarship's sake, where you spend your time, on trying to learn or whatever it is. So I would say, I need to read this thing in order to attack this problem. And after some time, we'll say, no, come on, let's get on and let's try to look at it and whatnot. So the scholarship was always in pursuit of research. And because he was looking at very central problems, you had to learn a really large amount of mathematics, but at the same time, try to continue to be involved in this research. It was a very difficult balancing act, which is difficult even now. But these are some of the very inspiring lessons. There are many more things, but I really felt very nice to have been a student. And of course, as I said, there are these difficulties from not being able to solve any of his questions, but that is a different thing. I also wish to thank Rama. It was wonderful dinners and hospitality, and it was really felt like being part of the household of Raghunathan. And even I remember being in Raghunathan's place, and Raghunathan cutting fruits and giving it to me as we discussed problems and other things. So it was a really very pleasant and very great experience too. Thank you both Raghunathan and Rama, and wish you all the best in the years to come.
Thank you, Rajan. Let me next invite Kaushik, who's another TIFR, old TIFR and then university person who would like to say something. Hello, Kaushik.
Yeah. Hello.
Yeah.
As I said it 20 years ago, Raghunathan was a hero for me before I knew him. I was in Mysore University, and the people there told me, when you go to Tata Institute, you should learn things from Raghunathan. But unfortunately, when I came to TIFR, he was not there. He was in US. When we came back the next year, I became his student. Not a research student. I learned a lot of mathematics that he lectured on. But the most important thing about TIFR those days was it was a family. I think Nimish and Gopal Prasad, etc. have mentioned this. And one thanks all those people, Raghunathan and Rama in particular, many of the other senior people, they treated us as their kids. And thank you all. Thank you. Huh? I was old enough, but as mathematically we were kids, and at family level, we were friends and part of the family. This, I think, speaks quite a lot about the TIFR was and what these people, Raghunathan, etc., made it into. Thank you all. Thank you, Rama. Thank you, Raghunathan, in particular. Thank you, Dani.
Thank you, Kaushik. For the few words on this occasion. As you know, apart from TIFR, Raghunathan has also been was also associated with IIT for many years, 5 years, 5 years or more actually. And from IIT, I would like to invite Professor Neela Nataraj to say a few words on this.
Yeah, hello, good evening, everybody, and a very happy birthday to Raghunathan. So, till now, whatever reminiscences which we have been hearing about is about how people work with Raghunathan. So I didn't have an opportunity for that, but I've heard about Raghunathan since my college days. Unfortunately, like many here, I didn't have an opportunity to interact with him till he joined IIT Bombay. So I've been this person who has been observing him from far and was in awe of his personality, like many others. The first time I remember very clearly was when I met him in the corridor of mathematics department. So the very first time I addressed him as Professor Raghunathan, and first thing he did was to insist that I should call him Raghunathan and not Professor Raghunathan. So I was so impressed by his simplicity. The other thing which I remember very clearly is that since I stay outside the campus, I used to always carry lunch, and he was one person who would be also, he never used to go home for lunch, and I could see him even in the afternoons, walking along the corridor very swiftly, and it was very clear that he was thinking some mathematics while he was doing this walks. So during, I got an opportunity to interact with him more closely during my tenure as head of the department. And also when I started getting associated with NCM activities. For me, his infectious energy, simplicity, and approachability are three great qualities. And it really impressed me very much. And his passion for NCM, as everybody knows, is quite inspiring. So I think on behalf of Department of Mathematics and IIT Bombay, I would like to thank him for his contributions to the department and the institute at large. I think the institute has benefited immensely by his presence. And among other things, I would say the nation is benefiting still a lot through his contributions via NCM. And I hope this will continue. Wish you again a very, very happy birthday and long, happy and healthy life. Thank you.
Thank you, Neela, to speak on behalf of IIT especially. Maybe Professor Jugal Verma is also here, and I suppose he had a busy meetings, but maybe he would like to say a few words this around. Professor Jugal Verma.
Thank you, Professor Dani. So my association with Professor Raghunathan is a little bit non-mathematical. I wanted to learn some mathematics from him back in 1980 when my advisor at that time, who taught me something about Lie algebras and their representations, asked me to go to TIFR and learn from the best mathematician in the country. But it was not supposed to be, although I received an invitation to visit. But I then went to Purdue to do my PhD and learned very different subjects. After graduation, I again applied to Tata Institute, and very quickly I got a visiting position. But somehow decided to come to IIT Bombay and never thought that I will get a chance to be associated with him after many years. So in about 2003, I met Raghunathan at Harishchandra Research Institute when I had gone to a DST meeting to propose a sequence of instructional schools in all areas of mathematics. My proposal was rejected by DST. It was rather surprising and disappointing, but I met Raghunathan. He was there for the council meeting, I think. And he looked at my proposal and he said, this is good. Why don't you come to the NVHM meeting and make a presentation, and we will support this program. So it was rather surprising to me that he could make such a decision in a few minutes, which DST took more than 2 hours to reject. So that quality of Raghunathan is extremely rare. Administrators I have found they are extremely careful in making decisions and take long time. But that is not the case with Raghunathan. Raghunathan thinks mathematics fast, speaks fast, and he makes administrative decisions on the spot, and they turn out to be very, very useful. And later on, we realized that he was always right. So that decision that Raghunathan took back in 2003 slowly emerged as a one of the big programs of NVHM, and later on it became the National Center of Mathematics. I really thank myself that I came in touch with him for this outreach programs which are being done by IIT Bombay and TIFR. It is because of his vision and his capacity to think ahead of the times. When he was the head of NCM, the first head of NCM, we were all very happy that he will come to IIT Bombay. We benefited a great deal from his presence, and he was present in every single seminar, asking questions, very penetrating questions to his speaker. And due to his presence, we had very renowned visitors in our department, and we felt very happy that he spent 5 years here. We didn't want him to go just like that, and it was good that he became chairman of NCM, and he served for another 5 years. The National Center of Mathematics is basically because of his insight, and we are all very lucky to work under his leadership. I have learned a great deal from him about how to manage things, and I try to remember him whenever I'm I have difficulty in making decisions. It is very, very difficult to be like him. He's like a model at infinity, which we can all see and try to reach. In all our endeavors, like learning mathematics or producing mathematics or in administration, we are all extremely lucky to have a person like him, and I wish him a happy birthday and very long and healthy life, and I hope he will keep on inspiring young people by his example. Thank you, Raghunathan.
Thank you, Jugal. I have, I think, exhausted the list that I had, but I would like to invite those present to volunteer to say a few words that they may like. I don't seem to have any messages received about volunteering, but I'm sure there are people who want to say something. So please come forward if you would like to say something. Hello, Dr. Amia Bhagwat, are you there? Hello, Amia. Anyone else? Maybe I see Dipendra Prasad in the audience. Dipendra, would you like to say something?
Hello.
Hello, yes.
No, I was not.
We're not planning to. Okay.
To speak, but anyway,
Yeah.
I'm happy to.
Extempore is always the best.
No, I am happy to wish Professor Raghunathan a very happy 80th birthday. He has been much source of inspiration for, since I joined Tata Institute in 1980. And I certainly hope to continue getting inspired by him. It has been a while since I met him. I hope to see him soon. All right, so maybe I don't have so much to say, but yeah, the Tata Institute that we joined in the 1980s was more or less could be identified to Professor Raghunathan. He was present everywhere in all the lectures, on the third floor, in the canteen, and somehow as students, one wanted to sit with him in the canteen to have tea, and it was always a great inspiration. Thank you, Professor Raghunathan. Okay.
Thank you, Devendra. I think Parimala is also around, and she was hesitant, I think, for being shy or something, but maybe she would like to say a few words. Parimala, are you there?
Well, I'm overwhelmed with all the expressions so far I've been hearing. And indeed, I share with most of my colleagues and younger people the kind of thrill we had in looking up to Raghunathan during our student days and later on. And thank you, Raghunathan, and Rama too, who has been, she was my senior in college and she was my role model with respect to writing English and so on. Finally, I met her later on in the Tata Institute, and thank you, Rama, for all the friendship, and Raghunathan for everything. Thank you.
Thank you, Parimala. Maybe also Ms. Ramdas. Ramdas, would you like to say a few words?
I had not prepared anything to say a few words, but this is indeed a joyous occasion. It's been a great privilege to have known Raghunathan and Rama all these years. And what can I say? I mean, his energy, enthusiasm, approachability, helpfulness, and concern for mathematics at large in the country and everywhere, it's without bounds. And we are all in great debt to him. Also, it's been really a great pleasure to have known Raghunathan and Rama as friends. Rama particularly was quite close to her children when they were young, and even now I think they remember her fondly and will meet her given the chance. So thanks very much, and thank you to both Raghunathan and Rama, and all the best. And this is indeed a joyous occasion.
Thank you, Ramdas. Now, to all the words, let me add my own few words. It has been a great thing to have been associated with him all over through my career, as to sort of replicate what Margulis said. In fact, in a more stronger sense, my life would have been, it's unimaginable how my life would have been without becoming the student of Raghunathan and interacting with him on various fronts. There was not just mathematics, but various aspects of promoting mathematics and so on, administration, everything. I mean, in a way, I share the thoughts and ideas expressed by many people, but they have already been expressed. But let me just say, it has really been great to be associated with him in various ways. So we have spent, I think, more than 1 hour, and I'd finally like to request Professor Raghunathan to say a few words on this occasion in response to in response. Just please. Raghunathan.
Thank you, Dani. I'm overwhelmed by all that has been said on this occasion by many of you. I don't know how to respond really, because it's the extravagant compliments paid to me by all of you makes me nervous about saying anything. Let me first tell you that, first of all, this conference has given me great pleasure. I thank all of you who have taken the trouble to honor me by attending it. I found all the talks enjoyable and the expositions excellent. They were a morale booster for me as they rid me of my anxiety about being able to cope with more recent developments in my areas of interest. I'm deeply grateful to all the speakers for giving the talks and also for their nice comments about me. Forgive me for not offering my thanks individually. To the audience over the last 3 days, may I say that I feel honored by your being present at this meeting. Many of you who are present, I've not really known you. And of course, there are senior people more senior people whom I've known, people closer to my age. And of course, there have been some of my students whom I've known. But there are many of you who have taken the trouble to attend this conference, and I'm very grateful to you. I owe special thanks to Jugal, who first mooted the idea of celebrating my 80th birthday with a conference, and to the committee of Jugal, Suri, Sudhir, Sandeep, Neela, Dani, and Anish, which organized this event. I'm grateful to the technical committee, many of whose members whom I have not met, for the way the online meeting was run without glitches. And I feel greatly honored by the composition of the scientific committee. And I'm grateful to all the members, Dani, Lubotsky, Margulis, Parimala, Rajan, Rapinchuk, and Venkatramana, for their excellent work on it. Finally, let me thank those who sent me birthday wishes through chat, which I could not respond to, as I did not want to miss out on the ongoing talks. I've had an enjoyable 60 years in mathematics from the time I joined the TIFR as a graduate student. And I would like to take this opportunity to record my indebtedness to the many people who made those years pleasurable. In my years at TIFR, I learned a lot of mathematics from many senior students. I'm happy that one of them, Ramanan, has been attending this conference and was kind enough to say very flattering words about me. I count him, along with my thesis advisor, MSR Saman, as the most important influence mathematically, especially in my formative years. Gauri Shankaran, another student, at that time taught me a great deal in my first year and helped me adjust to life at TIFR. Then there was Paman Murthy, who made the atmosphere ever so lively. 3 of those senior students are unfortunately no more. Raghunathan, C.P. Ramanujan, and R.R. Sima. And from all these 3 people, I learned a lot of mathematics. And those that early training in mathematics is a matter of great pleasure for me, and certainly forged my attitude towards mathematics as a whole. Through all my 51 years at TIFR, my interaction with colleagues and students was an experience I continue to cherish. I'll say the same of the 6 years I spent at IIT Bombay and the present institution, CBS, where I've spent the last 3 or 4 years. So throughout, I've had excellent colleagues, and it has been a very fortunate thing that I've had them as my colleagues, and it has always enhanced my experience, enriched my experience. I regret that Professor M.S. Narasimhan and Professor C.S. Seshadri, who too was an important influence on me, are no more with us. My students contributed a great deal to enriching my mathematical life. And it was indeed a great pleasure interacting with them and watching them grow as mathematicians. Among them, I am happy to find that Gopal Prasad, Dani, Venkatramana, Rajan, and Suri are involved with this conference. As I said, teaching them was a great pleasure. There is an old statement by Bacon which says that it's unfortunate that the people whom we want to teach most are the ones who need our teaching least. This was true of all my students, and it's a pleasure teaching them, though they probably did not need me or any other teacher for their picking up mathematics. Well, some of you present spoke a little earlier, and I am very grateful for your speeches, for the extravagant praise you heaped on me. I think Alex, it is in Berkeley that we started our joint work, and you came up with this beautiful idea of U elements and proposed to characterize the unipotent elements purely group theoretically. And that's how it started. And so that joint work is began by your inspiring remarks to begin with. Margolis had very many kind of things to say, and I'm very proud of the fact that he says that I was one of the main influences. But vice versa, he has been one of the most important major influences in my mathematical development. He time and again proved things which I had tried very hard to prove. But he always came up with such beautiful proofs that my competitive instincts were suppressed, and all that I could do was to admire the man for his great mathematics. And then there are two other mathematicians who are not here. I mean, one of them is no more, who were a great source of inspiration for me, who essentially were the most important influences in my mathematics were Armand Borel and Jean-Pierre Serre. Both of them, their mathematical work was a source of great inspiration for me. And of course, I greatly admire them, as I do admire Margolis. Well, Gopal Prasad had many kind things to say to me and to my wife. And he was my first student at TIFR. Maybe there were other students, but he was the first student who got a degree with me. Others probably did not get the degree, but he was my first student. And I'm happy that I have such a good student as my first student. I don't think it's given to many people to find a student of such stature, a student who acquired such stature later, to be the first student. And my other students have also risen, and as I said, I watched them admiringly as they grew into greater and greater stature. Dani, of course, has said many kind words about me, and so did Rajan. But I have also benefited greatly from my association with them. In the process of teaching them, there were a lot of things I learned myself. I mean, there were very often the teaching amounted to discussion in which they could give me a feedback, and that certainly improved my own understanding of many aspects of mathematics. And then I have also been praised for my work as an administrator. I'm happy to get those compliments, but I think they're a little too extravagant. Well, I did whatever I wanted, whatever I was capable of, and I've been lucky in the sense that many of my spontaneous actions have turned out to be good. A good administrator probably would think more carefully before making decisions, but I had a tendency to be somewhat spontaneous, and lucky enough that my spontaneous actions proved to be right. Well, I think there are many other people who have had a big role in making my experience richer. Of course, there was Kaushik and Ramdas who also spoke this meeting, whose company I have immensely enjoyed and who also contributed greatly to my mathematical life. Let me thank all of them, and also let me thank all of you who have spoken about my wife as well, and I thank you all on her behalf. And I should say, Nimish was one of my later students. He was not technically my student, but he is my grand student. I suppose he did get a master's degree with me, and he was certainly one of my students with whom I enjoyed interacting immensely. There are other collaborators apart from Shahar Moses and Lubotsky, Howard Garland and John Milson, for instance, and they certainly contributed greatly to enriching my mathematical experience. And I, of course, certainly learned a great deal of mathematics from them, and especially in the early days, the collaboration with Howard Garland took place in 1968 and a little later in 1974 as well, while with Milson, it was in 68, 69, and it was a pleasurable experience. They were both excellent collaborators, generous in their sharing their ideas, and it was really indeed a great pleasure collaborating with them. So all these people have made my life as a mathematician really an extremely pleasurable experience. And I would like to thank all of you for that. As I said, I also want to thank many of you who have also talked about Rama's influence on you. And I would like to thank you all on our behalf. Thank you very much. And I think that's all I would like to say. And I wish you all a bright future without the menacing endemic, which I hope will leave us soon. Thank you.
Professor Dani, you are muted.
Thank you, Raghunathan. And with this, once again, I wish Raghunathan, on the behalf of all of us, a very happy birthday and many more fruitful and productive and inspirational years to come, and look forward to another such event, maybe at a more not necessarily not online, but something more in physical terms, hopefully. And so with that, let us close this session. Thank you, Raghunathan.
Thank you all.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Thank you, Shah.
Thank you. Thank you.
Thank you very
Bye,
much.
Nimish.
Thank you. Thank you, Sudhir.
Thank you, Raghunathan. Happy birthday.
Thank you, thank you.
अभी कहीं हाँ कहीं
Hi, Kolyut. Thank you.
Thank you, Raghunathan. It was a real great pleasure to see you and wish you all the best. To you and Rama, I am ever grateful. So it's really very kind of you to have taken me as a student.
Thank you, thank you. I was lucky to get you as a student.
Thank you, thank you.
So Raghunathan, again, congratulations and thank you for all your influence and for meeting with you. Okay.